All right. I think we're going to go ahead and get started, everyone. So take your seats and prepare for a really awesome session on microphysics and clouds. So our first speaker is Yuki Kano, who will be talking on the evaluation of cloud microphysics schemes in WRF for Hokuriku winter clouds using videosonde observations. Speakers, you'll have about 12 minutes to talk, and please try to leave a minute or two for questions. So thank you.
Good morning. I'm Yuki Kano from Central Research Institute of Electric Power Industry in Japan. My talk is about the comparison of hydrometer in clouds. So, Hokuriku winter clouds are maritime convective clouds formed around this area during cold outbreak from Eurasia continent. These clouds are characterized by small cape and lower cloud top, and sometimes cause heavy snowfall. The annual mean accumulated snowfall in Hokuriku area exceeds 300 centimeters. So you can imagine how severe the snowfall for this region. The Hokuriku winter clouds are also known to cause frequent lightning in winter. The occurrence in winter is quite rare. It frequently occurs only in 3 regions. One is here, Hokuriku area. The other 2 are at the west coast of Norway and downstream of Great Lakes in the United States. So for better prediction of heavy snowfall and lightning in winter, it's important to know how the Hokuriku winter clouds are expressed in numerical weather prediction model, and also how it's sensitive to the cloud microphysics schemes. So far, many studies have compared the cloud micro schemes in WRF with observations for winter snowfall cases. However, few studies compare the vertical profile of hydrometers because we need some kind of special observation to compare the vertical profile of hydrometers. This figure is one example from this paper. In this figure, the hydrometers from simulation is compared with ice and liquid water content from aircraft observation. For Hokuriku winter clouds, there are several observation campaigns, but as long as I know, there's no study that compares the several cloud microphysics schemes with observation. So in my study, we compare 6 cloud microphysics schemes in WRF with observation. Here, I will introduce a video zonde observation. Video zonde observation is similar to the radio zonde, but we attach a camera to a balloon and launch to the sky. That camera records a photo image of precipitation particle in the cloud. So we can directly see the precipitation particle in the cloud. The camera can observe particle size greater than 0.5 millimeter, so we can compare simulated snow and graupel and hail with observation. And the right figure is an example of the observation. You can see a small graupel particle with diameter of 2 or 3 millimeter. The observation was done at Kashiwazaki City, as you can see in the left figure in the red dot. It's a coastal city located in the Hokuriku area. From 3 winter observation, we have 59 vertical profile of videos on the observation. We have compared simulation with all 59 videos on the observation, and we found a systematic difference between the cloud microphysics scheme. But today time is limited, so I will only show the result from one cold outbreak event on 2010. And I also show some result from another cold outbreak case to compare the particle profile. Here is my work setup. We use was version 4.0. The resolution of the outer domain is 4.5 kilometer, and the inner domain is 1.5 kilometer. We use cumulus parameterization for outer domain, only for outer domain, and the initial and boundary conditions are from ERA5, reanalysis dataset. So we compared 6 bulk cloud microphysics schemes listed in this table. And the WSM scheme is a one moment scheme, so only mixing ratio was predicted. In Morrison scheme, Milgrant-Yo scheme, and NSL scheme, and these are full two moment scheme, so mixing ratio and number density are predicted for all hydrometers. And this is an overview of the cold outbreak case on 2010. And from the weather chart in the upper right figure, you can see a low pressure system located east of Japan, and northerly wind prevails. Northerly wind blows over the Japan Sea. And in the left figure, it's a temperature. And temperature was about 10 degrees C before the cold outbreak event, and drops to 0 degrees C during 18 hours. We have 2 videos on the observation before the temperature drop and 6 observations after the temperature drop. We observed the intermittent precipitation during this event that is caused by the small convective clouds, as you can see in the right bottom figure. We also observed many lightnings before the temperature drop. First, I compare the precipitation pattern. The observation, it's a 9-hour accumulated precipitation. The observation is from radar rain gauge analyzed precipitation product from Japan Meteorological Agency. The precipitation was high at south of the observation site, and the peak was about 70 millimeter. If we look at the simulation result, all 6 simulations will reproduce the spatial pattern of the precipitation pattern. But if we look at the peak value, WSM6 overestimates the precipitation peak. So next figure shows the evaluation of number density. For the left figure is for snow, and the middle figure is for grapple. And the black dot shows the observation with 500 meter winds. Then the color line shows from the simulation result. In the simulation, we average the number density for columns with cloud top temperature within 2 Kelvin from the observed cloud top temperature. So if we look at the observation, the number of density of snow was an order of magnitude larger than that for the grapple. But we cannot detect all the hydrometers in the cloud, so it will be better to compare the ratio of the number density. So right figure shows the ratio of snow to snow plus grapple number density. So if we look at the right figure, WSM6, WDM6, and Milgrant-Yo scheme will reproduce the ratio below 4 kilometer. But in NSSL scheme and Morrison scheme, the ratio is high. That is caused by the too few grapple in these schemes. Next figure also compares the number ratio, but here we brought the result for 7 cases. Here we only compare the altitude where the observed solid hydrometer number density is greatest. For example, in the upper left figure, the observed number density was highest at 3,250 meters. So we compare only at this altitude. In the observation, here we have 7 cases, and the observation is 0.5, which means that the snow was dominant in terms of the number density. Unfortunately, no scheme reproduces a number density ratio correctly across all cases. And Milgrant-Yo scheme has behave differently among these schemes because it has more grapple with small diameter. Next, we move on to the comparison of the mass density. Left figure shows the snow mass density, and all schemes overestimated the snow mass density. In the middle figure, most of the scheme underestimated the grapple mass density, except Milbrandt-Yeo scheme. The right figure shows the ratio of mass density where at latitude where observed solid hydrometer number density is greatest. Here, in terms of the mass ratio, the grapple was dominant, but no scheme can reproduce the ratio of mass density. Next figure also compares the mass density for different 7 cases. Here we have 7 cases, and grapple was dominant for 6 cases, and snow was dominant for 1 case in the left bottom figure. But again, no scheme can reproduce the ratio of mass density across all events. Particularly, snow was dominant across all events in Thompson and Morrison and NSSL scheme. This is another coordinate break result from another coordinate break case. And so we have 8 observations. In the first 4 observations, the grapple was dominant, and later 4 figure, the snow was dominant. But again, no scheme can reproduce the ratio of mass density. The Milbrandt-Yeo scheme is the only scheme and that changes the dominant hydrometer, dominant kind of hydrometer across case to case. So to explain the difference in the mass density across the cloud microphysics scheme, here I show the budget of the mixing ratio. Upper one is for the grapple and the lower one is for the snow. For the grapple, the main source for the grapple mixing density was the collection of cloud. So the liming process is dominant for all cases. The difference is only in the magnitude. For the snow, there is a difference in dominant process. In the Milbrandt-Yeo scheme, the deposition growth is a dominant process. On the other hand, in the Morrison and the NSSL scheme, the collection of cloud was the dominant process. So the analysis of mixing ratio budget is done only for 1 cases, but this kind of difference in the dominant process would explain the difference in the mixing ratio. So this is a summary. We compare 6 cloud microphysics scheme for Hokuriku winter clouds using videos on the observation. Unfortunately, no scheme has significant performance to simulate the vertical profile of mass density, but we found a systematic difference between the cloud microphysics scheme. For example, snow mass density always dominant in Thompson, Morrison, and NSSL scheme. In Milbrandt-Yeo scheme, the dominant ice hydrometer varies from case to case. That's all. Thank you for your attention.
All right, I think we have time for 1 question, if there are any. There's mics.
So you showed in your early slides the temperature drop. Did any of the schemes reproduce the temperature drop more accurately?
All the scheme correctly simulate the temperature drop. So for the temperature, there's no difference across the schemes.
Okay, thank you.
Thank you.
Maybe following along that lines, you also mentioned the lightning flashes, and there are lightning diagnostics. In WRF, have you used those diagnostics to see if there's any chance that,
You mean
for-
the lightning?
yeah. For the lightning.
Yeah, actually for this case, we use WRF to simulate the lightning. And for this case, the special pattern of the lightning was well reproduced with NSSL schemes. But the temporal change of the lightning was not very well reproduced.
The online person, yeah, if you have a question, please speak into the room.
Hi, good morning, everybody. This is Gordon Brooks from the 16th Weather Squadron in Offutt Air Force Base, Eastern Nebraska. Yuki, thank you for your talk. I was wondering if you ever varied the shortwave and or long wave parameterizations during your tests.
I only tested here. We use RRT MG scheme, and I haven't checked other results from other schemes.
All right. Let's thank our speaker and we'll move on to the next one.
Thank you.
All right, so our next speaker is Cliff Mass, who will be talking about a new warm rain parameterization for WRF and MPAS.
Thank you very much. There is a major deficiency in the warm rain schemes used in WRF and MPAS. And I'm going to talk about the deficiency and I'm going to talk about a solution. I want to make sure that you know that my co-author is Robert Conrick, a graduate student and postdoc at UW. Now he's working at Boeing and he did most of the work. So I want to give him most of the credit. Okay. Well, warm rain is very important throughout the world, and both for clouds and precipitation. And it's important in many ways. Here in the United States, in many places, the atmospheric river precipitation is often associated with warm rain. Flooding in Hawaii is often associated with warm rain. Freezing drizzle in Alaska associated with warm rain. And climate sensitivity is really affected by warm rain processes. And that includes really messing up the cloud distributions and albedo and climate models. So warm rain is very, very important. Unfortunately, there are problems in virtually every bulk microphysics parameterization with warm rain. We've known this back into the 1990s, going to the early days of MM5, the work I did with Brian Colley, looking at precipitation along the west coast of the United States. And when we had warm, moist air coming in, atmospheric rivers, we saw underprediction, substantial underprediction on the windward side of the barriers on the west coast. And this is not only the Northwest, this is the whole west coast. There's been a number of field experiments, one by Minder in 2008. We put rain gauges along the Olympics showing that during warm rain periods, we tend to underpredict precipitation substantially. We've seen this in South Korea. I can show you some examples in South America. I could spend a half an hour showing you all the places where warm rain is underpredicted significantly. Okay. At the UW, we've run WRF for many years, and generally using the Thompson scheme. And we've looked at the biases of precipitation. That's what the figure over there on the right shows. The bias for our 36-kilometer main, 12, 4, and 1.3. And the red indicates underprediction. And what we see is red underprediction on the western side of the coastal mountains. And resolution didn't help much. That's important. And of course, there's Hawaii, where people like to go. Warm rain is very frequent. And underprediction of warm rain that occurs as the trades approach the terrain barriers of Hawaii. That's something we've seen over and over again. And yes, I shouldn't just talk about WRF and MPAS. This is true of virtually every other modeling system that has bulk rain parameterizations. For instance, if you look at the UFS FE3, again, this is just an example, precipitation equilute. The pink dots indicate reality versus the ensemble mean for GEFs. Basically, the tremendous underprediction of all the members. So why do virtually all modeling systems underplay warm rain? Why? Well, we got some detailed taste of this during the Olympex experiment. We happened to, about 8 years ago, we had a field experiment where we had distrometers and lots of rain gauges, lots of observations along the windward side of the Olympics. And what we found is that during warm rain, we had too few drops, and the drops that were there were too large. Warm rain is often associated with large numbers of small raindrops, and the bulk schemes were not doing this. Too few drops too large. So what we have done is attempt to use observations and models, and I'll show you how we did it, to fix the warm rain problem. And this is Robert Conrick, and what we called it, we named this scheme after him, the RCON scheme, okay? Robert Conrick, okay. Okay, so what we did is we started with the Thomson-Eidhammer scheme, okay, that many of you use, okay? And we made some changes to it. And I'll give you the changes now before you fall asleep or something. Well, one thing is, the big thing is we changed the cloud water droplet size distribution from the usual gamma distribution to a log normal distribution. That's the key thing we've changed, okay? Gives us a wider distribution with more large drops. We changed the auto conversion, and we've made some other changes that we had to make because we changed the drop side distribution. Okay, well, here was a problem we had, okay? The key was the drop size distribution of clouds, but we didn't have any observations. There's very little aircraft data in clouds, especially over the western side of the mountains of the West Coast, because they can't fly there because of FAA regulations. So we didn't have the cloud drop size distribution. So what did we do? Instead of using observations, we used runs of a spectral bin model. We use the Hebrew University of Jerusalem bin model to simulate a number of events. And I should say that it did an extraordinarily good job. It didn't have the bias. That was a real hint. The spectral model didn't have this warm rain under prediction bias. Anyway, that's what we used. And I'm going to show you a little bit about the distributions. So drop diameter is on the x axis, and number of concentrations on the y. And what I want you to see is a few things. On the large side, where it's rain droplets, by the way, we're seeing here the log normal is the blue, a gamma distribution in cloud is the green, okay, and the SBM, the spectral bin model is the black, okay. What I want you to see is there was a very big difference on the cloud side, or the smaller droplet size, between the SBM and the gamma distribution used in Thomson. The Thomson, you see the green is the Thomson over there, okay, very narrow distribution, okay. Compare that to a log normal distribution, which is the blue one, okay. So basically, we did not have enough small droplets in the gamma distribution, while the spectral model, which we're going to claim is close to reality, it had many more small droplets, very close to a log normal distribution. On the rain side, they use an inverse exponential. That was true in both the spectral bin model and what's used by Thomson. So we're not going to fool around with this drop size distribution in rain. On the rain side, it's the cloud side that was crucial. Anyway, so we changed Thomson to use a log normal distribution for the cloud droplets. That's the big change, okay? And then we had to make some other modifications. We had to make some modifications to get the auto conversion between cloud droplets and rain. And, we used the Nickerson et al. Approach. And we had a few other changes we had to make, but basically we counted any cloud droplets that fell out, we counted as rain, which is not done in Thompson. Anyway, that's what we did. That's the change we made to Thompson. The main thing is the log normal. And how did it go? Well, we tested this for some major warm rain events during the Olympics experiment. We, just for a few months, then we did our extended period. Then we went to Hawaii, then we went to Alaska to test this new parameterization. And we used, an old version of WRF 4.22, the YSU PBL, et cetera, okay? And I'm going to show you 3 simulations. I'm going to show you the Archon, our new one, the control, which is the classic Thompson, and the SBM, okay, the spectral bin model. You can see both of these, all 3 of these, okay? And what I want to tell you is that, and I'm going to blow this up in a section. You see where I'm going to show you the inner domain over here. You see the little box over there, and I'm going to show you a comparison. The control is on the top, Archon is on the bottom. You can see the precipitation distribution. These are for 2 events. The heavy precipitation gets to the purple and stuff. What I want you to see is just for each case, there's a significant difference between the 2. And I also have a scatter diagram, simulated versus observed precipitation. Control and you can see the observing locations by the dots. You can see the correlation coefficient is 0.72 for the control, 0.91 for Archon. That's better. And the mean error is minus 1.83 under prediction to 0.42. Okay. So, and we can go in this other case, 0.71 to 0.87. And you can see the increase in precipitation. So it's doing the right thing. You can compare the bin model against Archon, and that's what's shown over here. And, basically the results are pretty similar. The bin model, the correlation between observed and simulated is 0.94. Archon, it's 0.91. Okay. It's very, very similar. So the bottom line of all this is you can get bin model performance at bulk model costs. Okay. So this is like a free lunch, folks. Okay. Free lunch. It's always good. Okay. What about the rain? What about the rain drop site distributions? I'm going to show you for the 2 cases over here. Observed is the black. We had distrometers at the surface, so we were able to get that. Archon is the green. The control, which is the old Thompson, is by the blue, and you can see how much more realistic the Archon is to the observed than Thompson. And by the way, the Archon is very similar to this spectral bin model, which is indicated by the blue. Okay, we did the same thing for not just, for a much more extended period, and the results are very similar. This is from 1 November to 15 December 2015. This is at 12-kilometer resolution. The mean error went, from the control, which is Thompson, minus 14.1 millimeters over the coastal zone to minus 4.5. If you only looked at stations within 50 kilometers of the coast, we had an under prediction of minus 23.8, and the Archon made it 0.6. I mean, this is tremendously positive. And I'll skip this over here. Okay, let's try someplace completely different. Let's go to Hawaii. Okay. And Hawaii you like warm rain, Hawaii's a good place, okay? Because you have the trade winds hitting the terrain. And so what we did is we decided let's try Kauai, which is a big topographic barrier. 1 kilometer domain center, this is a wharf centered over Kauai. And we looked at some events where we had the trade winds coming in, okay? And let me show you it over here, okay? So this is 2 events on top and bottom. The control, the Thompson is on the left, Archon is on the right. My God, you can see how much more precipitation. Look at the shading, right? Way more precipitation there for Archon. And the mean error went from minus 14.18 to minus 0.98, okay? And for the other case, minus 14.4 to 1.76. Tremendous improvement with this cheap parameterization. And what about Alaska? Okay, let's really prove this thing out. Okay. Well, as you may know, Alaska has some serious freezing rain events. Okay. And that's associated with in quotes, warm clouds. Okay. Warm cloud processes. And that's a real problem for the Weather Service. They don't have, they underpredict freezing rain. So here's the control on the left. That's the Thompson, Archon, and way more freezing rain. Okay. And it was much, much more accurate. So here's a blow up. You can see way more freezing rain in Archon. So let me summarize the yellows on, okay? We are introducing a new warm rain scheme, which is a modification of Thompson right now. And basically with the key things, we changed the cloud drop size distribution, okay? The precipitation performance was greatly improved. Basically, our precipitation is statistically indistinguishable from observation of the spectral bin model. This is true. The forecasts are improved both in short and long times. It's true that it works on where we develop the thing on the West Coast, but also places like Alaska and Hawaii. And it clearly we're producing rain microphysics that are more realistic. You know, better cloud drop size distribution, better rain drop size distribution. And, you know, I think this thing has a lot of promise. So we're waiting to get the final word whether this is accepted for publication, but we should find that out during the next few weeks. So let me end right there and open up to questions.
Right.
And Robert Conrick is working at Boeing right now.
Yeah, thanks for that great talk. So you talked about the computational performance qualitatively. Can you speak a little bit about it quantitatively?
It's no different than Thompson. I mean, you know, basically it's the same performance as Thompson is. So it's no longer or shorter. Yeah.
Yep.
But it's obviously much cheaper than than using a spectral bin model.
Hey, Cliff,
Hi.
so you showed it really improves warm rain. What does it screw up?
You know, that's a good question. And the answer is it doesn't seem to screw up anything. And one reason I know this is we ran over longer periods. You know, I have an ensemble at the UW, okay, that I've run for many years. I have a 4-kilometer ensemble. And one of the members is this scheme. And I checked that. So it is not screwing up anything.
So you think we can let it loose on global MPAS and
I think you should, because one thing we did do some experiments. We played with the GCM and we put it in. Warm rain is a real problem for global models, right? This will change the cloud field substantially, make it much better in the global models, which will be. So I think that's the other thing to apply this to is the global models. That's the next thing that needs to be tested carefully.
all right, thanks.
Sure.
I guess this could be implemented as an option within Thompson. Is it sufficiently close that you could just implement it within the Thompson scheme?
Yeah, I mean, I think there's no reason that this can't become an option. I mean, it seems very robust. I like testing things a long time to make sure they're robust, and it appears to be, right?
So you'd use Thompson for the ice phase and then
Right.
this for the.
Yeah, it's just changing the warm rain side of Thompson.
The other question I had was, it's counterintuitive that you have more small cloud droplets and you have more rain, because that usually goes the other way with pollution.
Yeah, that's the bizarre thing. You know, anybody who lives on the West Coast knows about this. You know, you can get lots of precipitation with warm rain. You just have a lot of droplets. I mean, a lot of the heaviest precipitation on the West Coast is associated, you know, with this kind of mega large number of small droplets. Are we okay in time? Or are we, and how long do we go?
Yeah, we'll get this question first over here. Sorry,
Okay.
Roy.
Cliff, really nice talk. Kind of really interesting results too. I do have
Thank
one
you.
question though. A lot of these events, I see you tested it in a lot of different areas, but to me, one thing they all have in common is the warm rain seems to be these shallower sort of drizzly events influenced by orography. Have you had a chance to look at it from more of a trade wind sort of pop-up cumulus convection? And do you think it would improve there or potentially make that worse, since that's where a lot of the original sort of auto conversion schemes are developed?
Well, I mean, a lot of the trade wind stuff is warm rain, right? And so these events here had, shallow convection in there. There was convection. It all wasn't stratiform for the Hawaii case. But we need to look at it more. Yeah,
Cool. Thanks.
sure.
Quick question, Roy.
Well, hey Cliff, I love your talk. It was great talk. We've run 40 years of WRF over the continental US, and we see the same thing in the Pacific Northwest.
Yeah.
So I think we're gonna try this scheme as soon as possible. However, I feel that the areas that you tested it are all pristine areas. When we look at California, we don't see this bias. So one thing we need to think about is, in order to address Falco's comment about whether you can put this in MPAS globally, is how is this linked to aerosol particles?
Well, we use the aerosol aware Thompson, and we did play around with how clean the air was a bit. We did vary that, and it didn't change the results.
Yeah, we can talk later.
Okay, we can talk later.
All right, I think for the
Yeah, thank you.
sake of time, we should move on. Okay, so our next speaker is Song-Yu Hong, who will be talking on a double moment cloud parameterization with in-cloud microphysical processes for use in weather forecasting.
This is the new double moment scheme developed in the NCAR PSL GSL collaboration. And this is history of the micro scheme development led by myself, starting from late 1990, came to be an NCAR Cloud 235, and then revised microphysics was introduced, became to be a WSM 356 schemes. Semi-Lagrangian sedimentary was introduced 2010, and then warm rain microphysics with the double moment was introduced 2010, and the hail was added. And recently, in-cloud microphysics for production term were introduced. That is for the analytical solution. And then we realized that the current operational GFL microphysics scheme also adopts the sum of ice microphysics from the WSM microphysics. And then is a WSM micro scheme was written about 20 years ago, and the WDM was about 10 years back. So it's about the time to update the scheme anyway. There is a, based on the accumulated realism for past 10 years, we set up the strategy all the way from the previous development and the finding in the literature, and then revised semi-Lagrangian, and the code was entirely rewritten for computational efficiency. Two major components are the in-cloud microphysics and the semi-Lagrangian sedimentation. We don't have a name yet, but it came to be tentatively we call the UFS microphysics because my salaries came from the UFS R2 project. So that is a cloudiness in reality. Obviously, we can say left panel, we can say it's a 33% in cloudy. And the right panel, 98%. But the microphysics computation, all the conventional by scheme assume that 100% cloudiness in computing cloud microphysics. So that it's better to have the term as in reality. That the question is how to do that. So that we set up the idea, all the microphysical process, source and sink term occur inside the cloud, whereas the sedimentation, chemical process, or the advection or PBL process treated with the grid mean scale. And then cloudiness, we can derive the relationship from the satellite observation and the aircraft observation, so that there is a one-to-one monotonic relationship between cloud fraction and the cloud water content. Then just use that value, and then input is in cloud value, and the output is multiply the cloud fraction to get grid mean values. And then this is the analytical solution. So that is just to, if you look at the auto conversion in the upper right, then solid line is 100% cloudiness, which is conventional, and dashed line is in cloud. So that auto conversion rate about twice faster than the conventional MPS scheme. And the semi-Lagrangian is proposed by the Zhang and Hong 2010. Is a monotonic mass conserving scheme. It has just a forward advection. Typical semi-Lagrangian finds the departure point by iterating the mean velocity from the arrival point. Instead of this one doesn't have any iteration. It has a terminal velocity arrival point using the velocity at the top and the bottom of the grid cell. So the volume can be expanded or shrinked, but the mass is exactly conserved. So that when we applied this semi-Lagrangian for double moment about nearly 14 years ago, we observed that number constant rain is very noisy, wiggled features. So that in WDM6, we used that QR and NR sedimentation by O'Lorian. And then we re-examined this so that there is a size sorting issue because the number of sediment is slower than the mass. Also, depth of vertical layer decrease. So that is even if we have a number of time step for sub-stepping is enough to prevent shear condition, it could be violated within the sub-time step. So that we did a systematic and the bin, we wrote the bin spectral sedimentation, which is a reference model. So that on the left is a bin model, upper is a rain, and upper is a mass, and row is a number concentration. For the Eulerian 1, Eulerian scheme, as in WDM6, is a serious mass deficit. If we compare the upper two panels, so that also number concentration is okay, but it's a WDM6 Euler suffer from serious deficit. Even if a VT is updated during sub time step, which was good enough in single momentum scheme. So that we did an experiment, one-day test, bin on the left, and Eulerian 2 is the maximum sub-stepping. Using the delta G is the minimum value, which is the lowest model level height. So the iteration number is a maximum, which is about 241 iteration. Eulerian 2 is realistic, and the semi-Lagrangian 1 is the, as in the Zhang and Hong implementation, semi-Lagrangian 2 is the size constraint and the smoothing vertical velocity, which is realistic now. So you can have two choices. Maximum iterations, Eulerian 2 or semi-Lagrangian 2, but it's semi-Lagrangian doesn't have any iteration, it's just a single time step, and then Eulerian has a 241 iterations. And then this is the 2D ideal square line test in WRF, MPS only, 1 kilometer seminar forecast, upper level reflected, and then compare WDM6. U1 is all the changes in the microphysics, including semi-Lagrangian. U1, 2, U2 is only in-cloud microphysics. You can see that just the shape is front and the convex activity enhanced by the U1, and then U2, the width of the convex band is narrower compared to the U1 and WDM6. And in general, U1 is a convection leading edge enhanced, and U2 minus U1 square width is narrowed. In general, impact of in-cloud microphysics is dominant. And this is a reflectivity. Upper is U2 and the bottom is WDM6. You can see the width of square line is much narrower in the new scheme. And in terms of a storm scale structure, if you look at the upper layer, we have a very well organized, slantwise front rear inflow jet. And WM6 is less organized. The flow front to rear inflow jet is up and down. This is an aerial effect from the 100 to 5,000 at the initial condition. You can see the number concentration increase with the increase of CCN. In general, this aerial effect are reasonably reproduced. As compared to the WN6 scheme, NC is increased, size of a cloud droplet is decreased, and the raindrop size is increased, which is compliant with airborne observation by the Lay et al. 2019. And then we implemented this in the UFS model, global model. And the first single column model, CCPP. In general, cloud ice is smaller than GFDL, but greater than Thomson. Snow is smaller than Thomson, but greater than GFDL. And then implemented into the 3D GFS model. UMP is GFS version 16, P8 physics. CCN is initialized at 100, and then aerosol is coupled with the following the study of a Kangedal 2819. And then we compare with the P8 control, which is P8 is GFS version 17 with the Thomson scheme. And this is a statistics for the, let's see, I think, sorry. Yeah, this summer case, July 5 cases. So that in terms of anomaly correlation coefficient at 500 hectopascal, pretty similar, but it's a northern hemisphere tropics. This scheme is outperforms than control, which is Thomson micro scheme. And then, but we look at the grid scale precipitation, and then we notice that too much enhanced light to precipitate over tropical ocean and unrealistic distribution of rainfall over tropical land, which in northern South America, we can see the kind of line structure rainfall. This is the apparent efficiency in cloud microphysics. I think mainly due to the larger time step, which is delta T is 1/52 in the 13-kilometer GFS. And then in general, in terms of water substances, liquid is increased compared to Thomson, and the ice is decreased. And the winter case, very same behavior as seen in summer cases. So that slight better with the time in the northern hemisphere, also tropics. This is the last slide. Work time is very important in operational implementation. GFM microphysics doesn't have a number concentration for product variable, and the Thomson micro scheme has a 2 additional number concentration, which is at 11.4% increase over GFM microphysics. The new scheme has a 3 parameter variable for number concentration with the aerosol coupled, but it's only 4.8% increase over current operational GFM microphysics. So that the scheme is under development, and possibly goal to be a candidate in UFS version 18. This is the to-do list this year. Okay, thank you for your attention.
Are dependent on the cloud fraction that the model produces.
Yeah.
I would be surprised if the GFS versions do a very good job of that in the intermediate regime. In other words, if it's 0 or 1, that's fine, but in the range in between, the model may not be doing a very good job of that. To what extent does that limit your performance? Do you need the model to do a better job of cloud fraction in order for your scheme to work well?
Yeah, this is just a cloud fraction for resident feedback is different than it is here, cloudiness. This cloudiness is just the inside scheme without communicating with the outside. So purely observation-based partial cloudiness to represent in-cloud microphysics inside microphysics scheme.
All right,
Okay.
thank you. Okay, so our next speaker is Barry Lin, who will be talking on an explicit microphysical and electrical charging model to study the effects of changing aerosol composition on the electric field and lightning distribution. Thank you.
Good morning. I just should thank my co-workers or colleagues, Edward Mansell, U of Yair, Al Ilovich, and Professor Alexander Kane, who I work with at the University, Hebrew University. So this is actually a study in progress. I'm going to present the progress part, and at the end, we'll talk about what still needs to be done. So our motivation for doing this is our goal to use SBM explicit elect. In other words, a spectral model with an explicit lightning scheme to understand why lightning superbolts occur. Now, lightning superbolts occur in the red part of the spectrum in terms of radio waves that are observed from space, or sorry, by the WWLN data set. And they tend to cause a lot of the damage. There are superbolts that basically lightning bolts that tend to blow things up or kill people in greater numbers when they hit the ground. So what are lightning superbolts? They're, as I said, it defines extremely powerful and rare discharges, which represent less than 0.001% of the energy distribution of lightning strokes on Earth. That's what Holdsworth found. And he concluded that they are, I'm not sure exactly why I have a discrepancy, but for strokes over 10 to 6 joules, 0.004%. Now, this is what he found with the woolen network. And we found something different in the Mediterranean Sea. So we're going to focus on the Mediterranean, Eastern Mediterranean, mostly in December, January, and February. And there's 6 seasons, although the data is only for 5, but now we have 6. And we use the Earth Network's total lightning network, which is connected now to the Israeli total lightning network. And we looked at peak, we get variables such as peak current, polarity, location, GPS time, and we can distinguish between intra-cloud and cloud to ground strokes. Our detection efficiency of cloud to ground lightning is greater than 90%. So why do thunderstorms vary? You have different thunderstorm types, and depending upon where you are. For example, in Florida, they tend to be very high, tall clouds. In New Mexico, a bit shorter. And then if you go to the Mediterranean, they tend to be about 12 kilometers in height. In Japan, where there's a lot of positive cloud to ground lightning, they are even shorter. So just like people, there are different sized convective clouds. So I take solace in that. Anyway, the daily distribution of spectral wind percentage, we are many days are much higher than 0.04%. You can see this here from June 2008. The percentage is 0.5%, 1%, 3.5%, and these are based on peak current. So we're looking at peak current greater than, I think, 200 kiloamps. So this is not radio waves. This is actually dividing things by current. So superbolts and normal lightning dependence, we have a figure showing their dependence on cloud depth. And it appears that superbolts appear more frequently when cloud depth is about 6 kilometers. And this suggests that the charge register for superbolt strokes is confined to the lower parts of thunderclouds. But really what it means is that the energy of the cloud is dissipated into the ground and not into intracloud lightning. So that's a very important distinction, because the more intracloud lightning you have, the less likely you're going to have a superbolt. There's only so much energy to go around in any particular cloud. So here's a figure that shows cloud to ground events and superbolt events from January 23rd to February 2nd. And notice how many superbolts there are. And they're covering much of the Mediterranean, also along the southern Mediterranean, even a few in the eastern Mediterranean. We're thinking there could be a connection between superbolts and ship tracks as well. And one reason we wanted to use a spectrum in microphysics is because you can vary the aerosol content, the aerosol type, dust, and much more easily than you can with this bulk parameterization. So we did a simulation with before as well with WRF Elect and NSSL with Ted's help. He programmed in the energy spectrum or the energy calculations of the cloud to ground events. And you see that on January 27th, 26th, and 25th, or the other way around, there were excessive numbers of simulated strong events. So we've actually probably simulated these super bolts, although we didn't do any changes to dust or aerosols. We just use the scheme as is, which suggests that their occurrences also function as synoptic characteristics. So getting to the other part of the story, the SBM elect coupled with WRF elect, and that's the key, is that we're calculating all the charging and their sedimentation by bins, but we are putting them into bulk values when we calculate the electric field. So we calculate the water content or the effective water content, depending upon the scheme. We use either Takahashi or Sanders charging for hydrometer bins. We charge large ice and small ice collisions bin by bin, snow with snow, grapple with grapple, grapple with snow, and snow and grapple. And we have diffusional transfer of hydrometers. We have collisions of hydrometers, which moves the charges up the hydrometer spectrum. We have sedimentation, breakup of raindrops and snowflakes, advection of hydrometers and their charges, calculate bulk values for, we then calculate the bulk values. We have electric field calculated, the single and 3D discharging and dissipation of charges. And what's interesting is that unlike a comment I received years ago about how we'd never be able to run SBM on any computer ever as a review for a proposal, we now run it at 1 kilometer resolution, even higher with the charging, which adds all additional bins, and we do it inside our little department. So it can be done, and we're doing it. I put that behind me, by the way, just so you know. So the we wanted to reproduce the case study that Alexander Farrow and Ted, et cetera, did back in 2012, but we're only looking at the squall line. And this was the radar mosaic where the system developed across Texas, Oklahoma, and Kansas and moved eastward hour by hour. So this is these are those observations. And these are the ETNL observations that they had, total lightning. You can see that there are locations within the squall line that have higher values of lightning magnitude, and you have places which are smaller, but some of them are within the stratiform, I assume. So we then simulated the SBM explicit elect with our microphysics, and we did it with the NSSL scheme, and we see differences. We expect differences, but we're not really trying to explain them yet till we get to the paper, which we hope to write soon. But the point that you should gather from this is that it actually all of our calculations actually do produce similar results, although not as intense lightning as the other scheme. We would also hope that our scheme, which will produce more realistic stratiform cloud, would also produce positive cloud to ground lightning paths from stratiform as well, but we're not getting into that now. Well, sorry, we do have cloud to ground positive in this. This is just a single hour. I should have noted that. And we do have negative cloud to ground, and we have intercloud as well. So depending, we were going to investigate this more later. So here is this spectrum explicit elect cloud water and cloud and mass contents and number contents. And you'll notice that this basically looks like a squall line with rain falling from the squall line, ice at upper levels, snow, and this is a stratiform cloud that has been blown off to the east. And with the what do you call it, with the NSSL scheme, you have you have similar but not quite the same. So there are going to be differences for that reason. Just to I think I repeated something. It was too late. But here is just, let me just go back right there. Okay, right. So that's not, I hope I'm going the wrong way. Sorry. These are cloud numbers on the right side, and on the right is then just right. This is not NSSL, I was correct. So this is the radar on the bottom right-hand corner, and those are the cloud numbers. So this is just, point is that we produce mass contents and we produce number contents. My apologies for that. And then if we compare SPM with NSSL, we have, again, similar simulation, but some differences. You can see them, but I wouldn't say they're significant unless we were to quantifiably compare these results. So the point is that both models are producing the squall line. So now we have the charging, and what's interesting about the charging is that we produced total charge in the bottom left-hand corner is less, overall less, and less diffuse. And our electric field is different. And interestingly, like our grapple charge and the third one from on the left-hand side is positive, and in hair scheme it's negative. And we have the reverse for small ice. And snow charging is different. So it could be just a function of the fact that one is calculating things explicitly and the other is not. Something as simple as that, but needs more investigation. So we don't really have an answer for that yet. But again, charging depends on size, and it depends on who's colliding with who, or which bins are colliding with which bins. So now we did some optical, acoustical, and we calculated the total energy again, which is optical, acoustic, and radiative radio waves. And you see for this case that intercloud lightning is actually producing a lot of, dissipating a lot of the energy. And the CG doesn't extend out to the Super Bowl, or maybe on the edge of it, as we had in the Mediterranean case. So the conclusions in future work, we coupled the spectrum and microphysics with an explicit charging scheme. And again, I have to thank Ted Mansell for that, because he corrected all of my errors, but he wouldn't have had the opportunity if I didn't make them. So he perhaps thanks me as well. Bulk values of bin hydrometer charges were used in the WRF electric box MG algorithm to calculate the electric field. Discharges are then obtained from the 3D discharge model, which I didn't mention before. And we find that we're producing realistic charging structures, at least total charges and lightning discharges, based on the paper that was published previously. And there are similarities and dissimilarities with the scheme. Both produce predominantly IC events and negative CG events. And it appears that the SBM produces a larger stratiform area, which is expected, which includes grapple. And then what we really would like to do is study the effect of dust and pollution on electrical charging in the Mediterranean, because that was the funded proposal from the Israeli Science Foundation. And our hypothesis is that the superbolts are associated with shallow convection with enhanced iced amounts due to dust and pollution. And we actually hope to find out soon. So if you were hoping to find out today, you'll have to ask me later. So thank you.
All right, any questions?
Yes, Barry, that was a great talk. Very fascinating, these super bolts. I've observed them in Northern Europe, of all places, but that's consistent with your story of less than 6 kilometers in shallow convection. But it's inconsistent with the idea that they're associated with dust and pollution, because Northern Europe is very clean. So anyways, my suggestion is to look at Northern Europe, because they have a lot of shallow convection. And I've seen the color of the lightning in Northern Europe is yellow, not white. And that could be associated with the Super Bowl.
Right, it's very interesting. But remember that with the NSSL simulation, we did not add any aerosols or dust. We just used the scheme as it was, and it seems to have produced super bolts. So our initial, it may be actually that dust creates more intracloud lightning, which then reduces the number of super bolts. That's what I think I've also discovered. So we had a hypothesis, and it seemed like the observations proved it to some extent incorrect. However, we still think that small dust could affect the ice content in shallow clouds, producing stronger SBs, but we won't know till we test it in the model.
Yeah, this is great, great work.
Thank you.
Really encourage you to keep going.
Thank you.
Right, any other questions? All right, thank you. Okay, the last speaker of our session is Daiwen Kang, who will be talking on development and assessment of lightning data assimilation in a grid scale microphysics scheme.
Thank you. How does this work? Let me see. Okay. I'm glad to have this opportunity to come here to present the work we have been doing at EPA. It's my first time to attend this workshop and my first time to come to this city. Come to the title, the lightning data simulation. It has been implemented several years ago with the French scheme in the convective scheme to be used in the subgrid convection. It's basically mostly applicable to the larger, middle to large grid resolutions, and it has become the routine applications for regulatory use and research use at EPA. About 2-3 months ago, my colleague Karen Alabata reached some of us to see, since this earlier application has proved to be successful, why don't we implement this scheme to the grid scale microphysics? And this led to this presentation. And I will come here to show only some preliminary results. First, let's talk about some background history. About 6-7 years ago, when Nick Hayes worked with us as a postdoctor, he implemented a simple lightning simulation technique as shown on the flow chart. In that, when lightning is present, we basically trigger the unstable layer by adding additional water vapor to force deep cloud convection. If there is no lightning is detected at the grid cell, there are 3 options he tried. The no suppress, that means let the KF scheme run as normal. The full suppress, just skip the grid cell, no convective and shallow only, and just only allow shallow convection. After a simple test, he ran 2 months, one in the summer 2012 and one in the winter 2023, and he joined the following conclusions. Basically, the lightning simulation with the shallow only option considerably improves the rainfall, rainfall prediction, as well as some other near surface meteorological variables. And he suggested that the KF deep convection with lightning present and allowing only shallow convection will be the best option. And at the end of this conclusion, he also pointed that the lightning simulation method presented in this study needed to be tested under additional conditions and longer simulation periods and different grid scales. And also at that time, he only used the National Lightning Detection Network lightning data that's only limited in the continental US. So to address the concerns he raised in his conclusion, we performed various sensitivity simulations by combining different conditions. And the conditions shown on the table at the top is that we chose the 2 domains, the corners 12-kilometer domain and the hemisphere, which is 108 kilometers horizontal spacing. We also look at the trigger, the KF trigger, K1, K2, and also the convection frequency update time, CUDT. The reason is I chose these two parameters because at the newspaper, his paper, he recommended to use one set of the value, while in the regular applications without linear simulation at EPA, they recommended another set of the value. I did the literature search, Google search. There's some results show up just mostly from the forum, user forum, talk about with value, with the user, whatever, but I couldn't find any official publications to show the results, which numbers I should use. That's why I combined these trigger values and the frequency, the update time to be included in these simulations. And also we use the lighting data from NRDN and the Woolen data, as the previous speaker already mentioned. For both the data set, first we applied to the corner simulations. Then for we use the Woolen data to run the hemispheric simulations. And here, this constituted about over 20 model sensitivity studies. Before I move to the results, and just briefly show the two lightning networks. The NRD network uses very high frequency radio wave for their detection, and they claimed to be larger than 95% detection efficiency for cloud to ground flashes. But it only mainly covers the continental US, as the center figure at the bottom shows. That's the domain. For the Woolen data, it has a global coverage. It uses a very low frequency video wave detection. Its detection efficiency varies from region to region, and depending on the energy of stroke. Therefore, the cloud ground stroke has 60 to 80% detection. For also, because lightning activities and convection has very strong seasonal and geographical patterns. So for the corners analysis, we split the corners region into 10 kilometer regions as shown on the top left figure. And for the hemispheric analysis, we conveniently picked up a few countries. This also used in other air quality analysis. To evaluate our model performance, we use the daily precipitation from the parameter elevation regression ID independent slopes model, the PRIMS product. And for the hemispheric evaluation, we use the NOVA climate prediction center CPC's global unified goals-based analysis of daily precipitation product. Here is the results for the sensitivity analysis. On the left figure is the correlation coefficient, and it is split into three square or rectangles. On the left is the base case. It's base case for also combination with the different trigger and CUDT values. In the middle is the linear simulation using NRDN data. On the right is linear simulation with Woolen data. Or different, each line represents the different kilometer region, and we also have the total, all the thick green, blue lines. As you can see, all the lightning simulation cases have higher correlation coefficient. Of course, NRD has higher detection efficiency, have higher correlation coefficients. On the right, to the right, on the top is the mean bias and the normalized mean bias, and on the bottom is the RMSE and the normalized mean RMSE. And similarly, you can see all the error and bias becomes better when we use the linear simulation. And one thing I want to point out for the base case, that base case is very sensitive to the trigger values. You can look at the mean bias is up and down, over prediction and under prediction. It depends on the trigger values. But when we apply the linear simulation, no matter which data set we use, the sensitivity to the trigger values and to the CUDT is all disappeared. And here is the hemispheric evaluation for the simulation. Here I only show the correlation coefficient for the different regions. On the center figure is for the US for the correlation coefficient, and in Canada, China, Mexico, and India on the right figures. As you can see, the warm color is basically all the lightning simulation cases during the warm months when lightning activity is prevalent, we have much better performance in terms of the correlation coefficient, except for Canada because there are few lightning activities occurred. And it happens across all the different regions. Again, the base cases are sensitive to the trigger values, but the RTA cases are not. Here we have show the spatial rainfall for July 2016 on this figure. On the top row is the two observation-based products. The A is the prism and the B is the CPC. This, apparently these two observation-based products are comparable to each other. In the second row, C and D is the simulation, the base simulation and the simulation with the NRDN data for the corners. And you can see the base case in the Ohio Valley Center, the rain, the orientation and the rain band is very scattered. But for the RTA case, it's much behaved and comparable while with the observational product. The third row shows the light RTA simulation with the warning data. On the E represents the simulation over the corners, is similar results compared with the NRDN, but on the F, the right is the 108 kilometer hemispheric simulation regraded into the 12 kilometer domain. But you can see there is a overestimation of precipitation is due to the large grid size, 108 kilometer, because this over triggered the precipitation because we grid the lightning into the 108 by 100 grid cell. When we have a lightning, it basically triggers the convection. And at the bottom, I will show two base cases for the hemispheric simulation. This shows the two different trigger values. The G is use trigger value 1, and the H, the last one, use trigger value 2. We found that when we use the trigger value 2 without lightning simulation, the model is very dry. Actually, in the summer months, it produced 40% less precipitation compared to the simulation using the trigger 1. Now come to the topic today, and this is we implemented the fine scale simulations, and this the two next slides provided by Karen, and I'm now this most theoretical derivation. What we used, we first defined some E-cape source layer RCL. This is the lifting condensation layer, and the EL is basically cloud top. We defined the cape factor based on two observations, because this is the 1200 comes from, because there's a maximum observed in trained cape is less than 1200. And then when the lightning is detected in the grid column, basically we define some saturation factor based on with respect to water and with to ice. And when we have lightning, basically we push nudge the water vapor mixing ratio towards saturation based on the conditions. And if there is no lightning, we remove all the grapple from the mixing ratio, since the lightning only exists due to grapple. And to nurture large-scale moisture and reduce nominator of PF scheme, we also made other maneuvers. And we'll move quick to look at the results. This is the preliminary results for July 2018. Use WRF model 4.3 and 3. On the top left is the prism On the top right is the base, and the the bottom is using the Morrison scheme, and the right bottom just combine both MDM and KF. As you can see, the base model significantly overestimate compared to the PRISM, and the lightning simulation has reduced the overestimation. Have a close look. We just take the difference of this base to PRISM and the RT simulations to PRISM, and this is the significant improvement for the total monthly rainfall. And here I come to the summary. So lightning simulation technique based on the wisdom lightning phase from ground network has been implemented and tested in the WRF KF convective scheme across regional to hemispheric scales. We have done this for the whole annual simulations. It now has been routinely used at EPA and elsewhere to provide meteorology input to air quality model. So the implementation and testing of RT on ground on grid scale map scheme is underway. Right now, today, I only presented the results from the 12 kilometer. We are still need to do the 4 and 1.3 kilometer spacing. Hopefully next workshop, we can have more results. So with the lightning data being readily available, the warning data, the satellite GRM data, so that technique should be applicable to broad applications and incorporate into the future of MPAS releases. I'm mentioning this because every time you have a new release, people ask for lightning simulation. I have to manually put the code into the new releases. So I feel the pain to doing this. So I strongly encourage to incorporate in the future of MPAS releases. And here is the last. Just want to show the disclaimer. That's regular. Thank you for your attention.
It wasn't clear to me if you have a separation between your assimilation period and your verification period. How long do you assimilate the lightning for? And then what period do you verify?
We use the 30 minutes data. The algorithm basically look for 15 minutes earlier, 15 after, which if there's a lightning detected, we just trigger the convection.
Verification is later, rainfall.
The work we will use the daily precipitation, not go to the direct hourly data.
How did you characterize the observation error here?
Rare.
Observation errors.
It just uses the daily precipitation data, grid style by grid style, for each day.
I mean, when you assimilated lightning data, you characterize your observation error, right? Because observations are not perfect either.
No, we just use the PRISM precipitation data. It's what?
With no errors.
What?
Without errors, you mean?
Yes, there is errors. What's your question? Yeah, we will talk. Yeah.
All right, any other questions? All right, well, we'll wrap up the session then. Thank you everyone for attending. Go get coffee.
Yeah, here we have a physics update, PBR layer session. We have a full presentation today, and Joe Wilson is talking about the MINN scheme. Joe.
Okay. Thanks. So first of all, I want to thank all the authors here listed. They were all contributed in some form, whether by discussion, testing, or direct code modifications. I just want to give a little bit of a brief overview of what the MYNN EDMF is, so we're all on the same page, and then discuss some of the major improvements that have went in since there's been like a 4-year gap without any updates to the MYNN. So there's been a lot of changes. I want to convince you that you should be running the 4.5 plus version, and then I'll summarize with some results. So the MYNN is now, it's been an EDMF scheme for many years now. It's basically the eddy diffusivity component is a turbulent kinetic energy scheme, which has options to run at 3 different closure levels. I'll talk about level 2.6 later on, but I'll just note that level 2.5 and 2.6 are designed to run with the mass flux scheme. The level 3 closure should not be run with the mass flux scheme because that has its own non-local attributes. The mass flux scheme itself is a 10 plume model, or at least has a potential to run 10 different plumes. Not all are active at a given time. They're discrete sizes between 100 and 1,000. And basically the number of plumes used at a given time step is determined by the environmental conditions as well as the model configuration. So after the number is chosen, each of these plumes differ only by their lateral entrainment rates, since it's inversely proportional to the width. The biggest plumes will have the smallest entrainment and basically penetrate up higher. And any plume that passes the lift and condensation level can create shallow cumulus clouds, and the scheme's only active in convective conditions. So for the first decade, the MYNN has existed in warfare W. It's been primarily developed in the scope of the RAP and the HER. And this is basically consists of, short range forecasting within the RAP HER suite, our 50 vertical levels. And a lot of the development was driven basically on, CONUS or land specific stats. So that's still our business today, but we also have expanded our scope considerably into the global realm, where now we have the MYNN in multiple die cores, testing it in multiple suites, different vertical levels, et cetera, and looking at longer term forecasts, which we never really did in the past. So obviously the emphasis here is on trying to get the MYNN to work for a wider variety of applications at all scales with heightened performance on these metrics that are important for global forecasting. So one of the first things we did in the past few years is this code restructuring. And this is basically also called like CCPPizing the code, which is basically consists of this new wrapper that's in there now. It's basically an interface between the PBL driver and the scheme itself, which basically translates any die core specific variables to whatever the MYNN expects and backwards, and handles any nameless options that may not exist in certain die cores. And then there's also this common file that basically, and this is also die core specific. It's going to use the same physical constants that are used by all the other schemes within the die core, as well as some extra MYNN specific constants. And the MYNN scheme itself has been reorganized a little bit, and it's now an IK scheme instead of a IKJ. So right now I can't just copy over a version of MYNN from the CCPP into WRF and vice versa, because there are other issues that can't fully universalize it, but it's really close now, such that I can at least make updates far more frequently than I have been in the past few years. One of the biggest improvements we made, and this really showed up in our long-term forecast when we first started doing global forecasts, with cold moist biases basically really setting in by day 5. And, without ever testing this thoroughly, it was, a bit of a surprise for us, but it turns out there were some conservation problems specifically within the mass flux scheme. And we're also naively, zeroing out some negative tendencies instead of treating them properly. So together, this made some conservation issues. So you'll see in the WRF 4.2 code, lost the pointer. Whoops. Anyway, well, so basically we couldn't get a match between the surface fluxes of heat and moisture and the integrated water content delta and heat content delta, whereas now we can to a good degree of accuracy. There's also been an important TK budget fix. This is only in the output, the diagnostic output. This doesn't affect how the scheme was running, but this is good work from a colleague, Franciana Pujales, we had some kind of gross approximations in this vertical transport term here. And he basically fixed it. So now each term is within higher, basically the same as what's used in the actual TK integration. There's a new downdraft mass flux scheme that's coupled to the cloud top radiative cooling, but it's coded right now to be inactive, and I suggest to keep it that way until I finish it, because actually it's still under development. I'll just keep it at that. We've known of this overshooting plume problem in the past. Other colleagues, George Bryan and specifically has called it out in the past. We revised the entrainment rates and eliminated this problem. Here's just an example of 10 different cases taken from the LASSO data set. These are all continental shallow Q over the Southern Great Plains site. Here we're showing some LES runs match up against some single column model runs using the MYNN. They're all forced with the same forcing. We'll note though that there's a difference between there's grid mean mixing ratios here on the LES versus in-cloud mixing ratios here on the right. So we're not really this top heavy. In reality, if you multiply this by cloud fraction, they will resemble each other, but you still get a lot. If you look at the silhouette of these clouds, you can see, the onset, termination, cloud base, and depth. For most of these cases, we get a pretty good match, and there's no hint of that overshooting plume problem anymore. Wayne Angevine will talk a little bit more about this in a couple talks later this session. Okay, the new closure. This is so if you recall in the past, you've set this nameless flag for decide which scheme you're going to run, basically. And MYNN ran with option 5 for the 2.5 and level 3 for the 6. We now vacated 6, so now you only use option 5, and then you use this new MYNN closure nameless variable to regulate the closures. And we added this 2.6 because we wanted to prognose Q prime squared, the total water variance, because it's important for use in our cloud PDFs. And this is our new cloud PDF here on the right. We're getting away from this first order form where the standard deviation of the saturation deficit was according to this first order form. Now we're just taking the square root of our prognosed Q prime squared, and we divide the saturation deficit by that to get our normalized saturation deficit, which is the primary variable for this cloud fraction function for this stratiform cloud component. Here's just an example of one case from a WRF-based perspective. If you download the 4.5 code top of the trunk right now, this is the overall cloud evolution you get. There's an hour 12 forecast match up against the visible satellite imagery. You can see that overall the shallow Q is done reasonably well. One thing we have struggled with in the past is our cirrus, our upper level clouds. We know part of that is the Thompson because it's pretty lean and it's upper level ice clouds. But we should be able to squeeze a little bit more out of that than what we're getting from our subgrid clouds. And there's been some small tweaks to help us in the right direction there. It also helps, some of our intermountain west convection is a little bit thicker than before. And the marine clouds are a little bit thicker than before as well. So this set of updates, this shows a WRF-based perspective on how we're tweaking our clouds in the right direction to give us better overall global forecasts of global radiation means. And speaking of global forecasts here, we run a version of the GFS with the MYNN put in, replacing the GFS boundary layer scheme and shallow cumulus scheme. And that is here in the gold, basically. And we also run a version with the GF convection scheme, replacing the SAS convection scheme. So 2 versions of the GFS. And for last year's hurricane season, during this entire period, we did have smaller overall hurricane track errors with the MYNN version in both basins, the Atlantic and the Pacific. But the wind speed errors were slightly low bias, a little bit weak bias in general. The GFS was too in the Atlantic, but MY9 was a little bit more negative bias. However, in the East Pacific is a little bit of a trade-off. Did better at some forecast hours. The GFS was a little bit high. And for the same period, look at the 500 millibar anomaly correlations here. Basically, both of the versions with the MYNN and a difference from the GFS shows an improvement in 500 millibar anomalies. Most of that's coming from the southern hemisphere. There's just some evidence that the MYNN is maturing more for the global framework. There's some optimization work going on since we updated code into 4.5, and this is basically have it running about 10 to 15% faster on CPUs. There's been further work to get it GPUized. We got some pretty impressive speed ups here, but some of this structural code change has actually ended up negating some of our CPU changes, actually slowing it down for CPUs. So we're still working on that. I'm not going to check in anything that's going to slow down CPU, since I think there's still a lot of users. They're going to be using CPUs for the near future. But in summary, I think that this MYN code, it's been implemented in at least 5 different die cores that I'm aware of. And this expanded testing has really helped improve the skill overall. Now that the code is more universalized, it's going to be easier to make more frequent updates. I have already talked about some of the improvements we made. I probably shouldn't have said we removed all major deficiencies. There's still obviously forecast issues like winds and, that's a little bit excessive there. Apologies. But thus far, this cross I-core development has been successful, although it's been a lot more challenging from just a code management perspective. But we could say, obviously I need to learn a lot more about how it's behaving across die cores, but it's conceivable that if we learn a little bit more, it requires special tuning for different die cores. That's possible. So we could do it, but I think a lot more needs to be learned before we get to that point. All right, that's it. Thanks.
I stop. Question and comments?
Joe, so I have 2 questions. In the past, and talking about global scale forecast, my understanding is that we need to not have shallow convections from available convection scheme when we use EDMF, because the shallow convection would be overestimated when we use both subgrid scale convections and the Moynihan scheme. Is it still the case?
Yeah, we definitely do not use a shallow cumulus scheme with the EDMF. They end up fighting each other more than anything else. So what I see more often than not as a degradation in clouds when we activate a shallow cumulus scheme at the same time, because it's designed to do all that work itself. So if you share the load with another scheme, you're never going to get as good of results.
So that's what I used to do. And then the second question is, you were talking about cirrus cloud, and because coming from the Thomson microphysics or something like that, does that imply that your formulations of the cloud fractions when you use MYNN replaces all quantizations of the cloud fraction?
So the MYNN does provide all the cloud fractions. Yes, but so if there's a resolved scale cloud there, if Thomson is producing an ice cloud, it's in general, it's too thin, and we'll use its mixing ratios. We'll default to its mixing ratios versus what's predicted in the MYNN when the microphysics scheme is creating that cloud. And more often than not, when that happens, is the ice water paths are so thin, they just have a very small radiative impact with Thomson. Not all the time, but commonly.
Okay, then thank you very much. Let's move on to the next speaker. Xiaotang from the GSL. same division with the Joe. Talking about the evaluation of MON scheme in the GFS and WRF.
Hello, everyone. My name is Xia Sun. I'm a research scientist at the series at CO Boulder. I work at NOAA GSL. Today, I'm going to show some results on our recent work on the verification of the M1NN EDMF PBL scheme on simulating the marine boundary layer clouds using both WRF ARW and FV3. I would like to acknowledge my co-authors listed here for their contributing. So here's the outline of today's work. I'll provide some background information which motivates today's work. And the Eureka 4A is a field study which provides a verification data set we use for today. And the model configurations using FV3 limited error model and the WRF ARW. So the last is the results and summary. So trade wind clouds has been shown to display the different patterns at the mesoscale. So let's see. So these 4 panels show the 4 different cloud patterns identified by Stevens et al. So it has the first kind is a sugar cloud. It kind of had this dust form with no self-organization, and the gravel cloud began to have some kind of organization along the lines and arcs. So for the fish, it has this clear fish bone-like cloud structure, and the flowers has the distinct boundaries shown between the different flower cloud structures. There will be some similarities exist between the sugar and the gravel, flower, and the fish. Boni et al. Tried to investigate whether the different cloud patterns will have the different impact on the net cloud radiation effect. So they use the daily means of the net CRE derived from the series dataset and the low-level cloud amount from the Moody's cloud products over 20 years. And they found that the different cloud patterns are usually associated with a different cloud cover, thus have the different net CRE impact. So for example, for this sugar, it usually associated with a low-level cloud cover of around like 16%, that associated with a net CRE of like -6 watts per square meter. And for the flowers, it has usually associated with a 35% low-level cloud cover with a net CRE of -15 watts per square meter. So another main motivation for our work is that we would like a unified M1N EDMF scheme that can perform well across the different decors. So initially, M1N is mainly developed under the WRF framework. So with its recent use in the operational models, we want to make sure it also works with other decors. So this will benefit both the model developers and the researchers. So here is a brief description of how M1N EDMF differs in NRW and FV3. So for the left column in WRF, it uses explicit dimension declaration and optional variables, while in FV3 within the CCPP framework, it uses assumed shape array declarations and handles the option arrays in the meta file. So this won't necessarily lead to any simulation differences. So the second aspect is that in WRF it uses the dry mixing ratio. So as a state variable, this means that in WRF it will require one more conversion to specific humidity than CCPP. So the last one is that in WRF it has the moist variables to radiation scheme as grid means. It will need the conversion in the radiation scheme to convert it to in-cloud values. So in the bottom, I listed a link for a brief overview for FV3 dynamic core from the GFDL FV3 team. Okay. So here is a model configuration we set up for ARW and the FV3 limited area model. For the WRF, we use the pre-version 4.5 it was pretty close to the final version. So we set up two nested domain with a horizontal resolution as 12 kilometer and 3 kilometer. So this is the illustration of the domain setup. So for FV3 limited area model, we use the unified forecast system short range weather application. So for the public release version of the SRW app, the nested capability is not supported at this time yet, but we know it's supported by FV3 and in the UFS hurricane application. So it's possible it will be added for the SRW application. So, but at this time, we have to conduct separate simulations with horizontal resolution of 12 kilometer and 3 kilometer to be consistent with what we did in WRF. So for the first thing, we use the GFS analysis. We did check how Euro 5 looks like as a forcing data set for WRF. It does look better than GFS, but due to the current limitations of this SRW application, we'll have to both use GFS analysis. So the other common configurations, including the M1NN EDMF PBL scheme, Thomson microphysics, M1NN surface layer scheme, and NOAA-MP. For the radiation, we use RTMG. So we set up a vertical levels of 65, which is consistent with the Rufus currently developed at NOAA. And we conduct a simulation length of 48 hours with a time step with 60 and 18 seconds for the two domains. So our simulations was initiated as the UTC before the IOP, and the forecast hour of 42 is examined. So the Eureka 4A, the full name is elucidating the role of cloud circulation coupling in climate field campaign. It was conducted in January to February 2020 and located at the south and east of Barbados. So here is the location of the Barbados Cloud Observatory. So this plot on the right shows the available soundings, including drop sounds from aircraft and the radio sounds from research vessels. So for our work, we use the data set from drop sounds from the Halo airplane, which is in this green circle. It also called the Eureka circle. And we use the sea surface temperature from the research vessels of this media in this cyan color. So the other data we use also include the MODIS satellite images and the liquid water pass derived from the GOES 16 satellite data and the 1 degree hourly series S1N data. So here's a overview of the three cases we checked in our work. The February 2nd case, February 7th case, and February 9th case. So the first row is MODIS satellite image at 18 UTC on that day. And FV3 and the following two rows are from the FV3 3 kilometer run and the WRF 3 kilometer run. And we showed the spatial distribution of the outgoing shortwave radiation at the TOA. So basically, we see that for the fish cloud, both two models is able to capture the position of this fish cloud, although maybe losing some fine scale structures. For the sugar and gravel, it can be also roughly captured by the model. And for the flowers, sometimes the model is able to capture the position, the presence of the flower, but sometimes the sizes of the flower structure and the spacing between the flowers can be like different in the model. So we labeled the two places for the GOES domain, which is labeled in this orange rectangle. We will check the liquid water pass. And this Eureka cycle, we will like verify the sounding profiles. So here is an overview for the vertical profiles for the three cases. For the potential temperature, water vapor mixing ratio, and wind speed for the three cases. So the black line are the averages from the Eureka for a drop sound from the Halo. and then the colored lines from the four model scenarios. So the drop sounds around the Eureka circle is usually spanning several hours. So we are comparing it against to each, for each drop sound, it is compared to its closest hour simulations. So we see that overall the meteorological variables are well simulated in both FV3 and WRF. So if we see closer, there is actually cold bias exist within the lowest 100 hectopascal above the surface. So there are mixed results for water vapor mixing ratio. For example, for the February 2nd case, there is like overall dry bias below 800 hectopascal. However, there is like moist bias for the February 7th case. So here is the sounding statistics. We showed the verifications below the 850 hectopascal for all three cases. So this pertains to a total of 234 sounding profiles. And we see that, so this blue color means negative bias and the red color means positive bias. And this bold represents the best performance, which goes to WRF 3 kilometer run. So there is overall negative biases for the potential temperature in the boundary layer. However, mixed results showed up for the water vapor mixing ratio with WRF generating moist bias and FV3 have like dry bias. And there are like stronger wind simulated within the boundary layer. So for the cold bias within the boundary layer, we checked a bit how like the forcing data set will contribute to this cold bias within the boundary layer. So here is a comparison from the research vessel MET and the sea surface temperature from the Euro 5, which is this orange color, and SST from GFS analysis, which is this green color. So we see that overall, both forcing data set will have like a cold bias already exist in the initial conditions, with GFS analysis have like a mean error of negative 0.7 K. But we understand there is like sampling error when the research vessel is measuring the sea surface temperature, but this like at least partly contributes to the cold bias. So here's the liquid water pass from ghost domain we showed from the orange rectangle for the three cases. So the x-axis is the different percentiles from 0 to 100%, and the y-axis is the liquid water pass for the three cases. Again, the black color is from the ghost estimates, and the colored lines are from the four model simulations. So for the liquid water pass, we use this criteria to include the subgrid scale contribution. So we see that at the ghost domain, FV3 runs, which is this green and red color, Euro generates more liquid water pass than WRF runs. So this is related to the more subgrid scale cloud water generated in FV3 compared with WRF. So if we have to pick one, we see that FV3 kilometer, which is showing this red color, is more similar to GOES estimates. So for the WRF runs, which is this orange and blue color, it generates less liquid water pass than GOES, except for the last case, which performs reasonably well compared with the GOES PDF. So for this slides, we checked how the model like performs in simulates the transition between the small to medium cumuli. So we did a cross section from point N to point B, and we calculated the total condensate in the WRF model and the FV3. So we see that in both models, they can capture the transition pretty well, based on those total condensate variables. So next we check how the net cloud radiative effect looks like for the different cloud patterns and how they looks like in our four model simulations. So on the left is a spatial distribution of the net CRE. So we derived it from the 1 hour hourly series data in 1 degree resolution. And we manually draw these grid boxes based on the multi-satellite image we showed in our last slides. So this blue grid box is fish pattern, and this green is sugar, and this red is flour. So we see that there is more net CRE was shown in the fish pattern compared with the fish and compared with the sugar and the flour. So on the red side of this slide, we show the net CRE from the series derived from series data set compared with the 4 model simulations. So consistent with the series, all simulations generates the largest net CRE for the fish cloud. For the FV3 runs, which is this red and green color, overestimated this net CRE for the fish pattern, and the WRF runs underestimated. So, however, for the sugar and the cloud pattern, WRF simulated the best net CRE compared with FV3 runs. So in summary, we used the same version of M1 and EDMF in WRF ARW and FV3. So they both show reasonable skills in simulating the cloud structure in the 3 cases we selected. And both WRF and FV3 have the cold bias and the stronger wind speed within the boundary layer. However, WRF has moist bias in simulating the water vapor mixing ratio, and FV3 has a dry bias within the boundary layer. So the WRF runs generated a liquid water paths that are smaller than the goals estimates, while FV3 12 kilometer Euro generates the clouds with much higher liquid water paths than seen in observations. So the net CRE varies with the different cloud patterns, and this variation is captured by the models. Flowers and sugar were best simulated in WRF regarding to the net CRE. So the accurate cloud simulations for every type of cloud at all model resolutions might be challenged at this time, and more work will be done to see if we can better optimize M1 performance for each die core. That's it. Thanks.
Running over time, can I pick question?
Very nice work. I like to see the inter-model comparisons. Just a quick technical question. Do you know what the divergent dampening order was set to? Was it N or equals 3 or 2 or 1, or do you know? For the filtering?
The filtering in which?
I'm sorry, FE3 die core.
Oh, I didn't. I think I used the default options.
Okay, well, I mean, that has a definite impact on the size of the clouds that you get. Not that it's a fix for everything, but you might want to look at that, or we can talk later then. Thanks.
Okay, I'll go check it out. Okay.
Thank you.
Okay,
On to the next speaker. Wayne Engevin from the NCAR. We'll talk about the subscale EDMF, MIN in EDMF.
Okay, so
And
forward.
this
back.
is the point.
Okay, I probably won't try to use the pointer. So Joe gave an overview of EDMF, and Shia gave some analysis of a particular large scale cloud case. I'm mostly going to talk about smaller scale, but looking at several different cloud regimes. And down kind of in the guts of the model, how can we best estimate the subgrid cloud fraction and the condensate mixing ratios in an EDMF scheme? So I'm going to look at shallow cumulus cases from LASSO, which I first heard about at one of these workshops several years ago, and has been very productive for me. And then I'm also going to show a couple of results from the MAGIC campaign in the Pacific. So the traditional method of
estimating the cloud fraction and the condensate is by estimating a relevant width of the PDF of saturation and relating that to those variables. The problem is that in shallow cumulus conditions, estimating the relevant width of that PDF is difficult. As you get to larger cloud fractions, it gets better. So the improvement that I'm proposing is to make use of the updraft properties that we're calculating in the mass flux part of the EDMF scheme. And the key insight is that the cloud and the condensate can be conceptually modeled as the product of a source term, something that produces the cloud, and a lifetime, that the cloud erodes in a specific amount of time. So that's the talk. You can all go to sleep now. So the rest is just details. The conventional approach, one conventional approach is Chabriot and Bechtold. And you can see here now the plot of the saturation, the normalized saturation deficit on the x-axis versus the cloud fraction. And this is from some LAS runs that I did in SAM. And you can see what some of the difficulties are. So the part that we're interested in here is just to the left of 0, where you have small cloud fractions. And you can see that there's a lot of scatter on the vertical axis there. And the red line is the traditional, is the Chabriot and Bechtold function from their paper. I put a yellow line on there that's a different fit that fits a little better, but I can't guarantee that it's, in any sense universal. So, and the other problem that you can see is that the slope of that curve is very steep in the region that we're interested in. And that means that a small error in the state variables, so a small error in your saturation deficit, is magnified into a large error in cloud fraction. And as I also mentioned earlier, the width of the distribution, which goes into the denominator on the x-axis there, is also not easily estimated. I'm going to elaborate on that at some length here. So now these are histograms versus height of the saturation deficit. This is one of my favorite lasso cases. In the color plot shows the frequency of occurrence of each saturation deficit value versus height, plotted by height. And you can see where the 0 line is the vertical line. That's grid scale saturation. And then the horizontal line is where cloud base is. So, and then I've taken a slice across the middle of the cloud and plotted that on the lower plot. And you can see that it's a bimodal distribution and that the horizontal lines that represent the standard deviation or the interquartile range are not a useful estimate of the part of that PDF that we're interested in. Here's another case. This is actually from the MAGIC campaign. So it's more or less stratocumulus over cumulus. We have two, we have a single cloud layer with 2 peaks of cloud fraction. And again, you can see that these distributions are both bimodal, but they're different depending on what the cloud fraction is. And again, the sigma is not necessarily a very good way to estimate the saturated part of that PDF. Here's another one. Now in the upper layer, the cloud fraction is approaching 1. And so in the far upper right, you can see that the bimodality of the PDF has more or less disappeared. And now you actually can use the standard deviation of that to estimate the interesting part of the PDF. In the LES now, I'm trying to find a better way to do this. So in the LES, it turns out that particularly in shallow cumulus cases, the cloud fraction is extremely well predicted by the area of the saturated updrafts. Not a big surprise once you've seen it. And the condensate is very well predicted by the mixing ratio in the saturated updrafts multiplied by the area of the saturated updrafts. So this is our source term. Basically, the saturated updrafts produce the cloud, and then they are eroded fairly quickly in this case. And the rate of erosion is expressed by the slope of those fitted lines. And so in this case, it's pretty quick. The slope of the fitted line is 1.2 or 1.15. And that means that the clouds are eroding quite quickly. To connect that to the EDMF, we need to know how well the mass flux part of the EDMF scheme is representing the updrafts that we see in the LES. So the updraft properties are available. We know we're estimating an area, a mass flux, a condensate value, and temperature and vapor differences. So on the upper right, on the upper two rows, you see the fraction and the fraction times condensate from SAM, and this is the composite of 15 cases. We deliberately represent less than all of the updrafts in EDMF. So it represents only some fraction of the strongest updrafts. And we see that in these composites. And then on the bottom, I've plotted one single case so that you can see that I'm not cheating too much by showing the composites. In MYNN EDMF, the updrafts are discrete, but the smaller, weaker updrafts terminate lower. So we actually get a somewhat smooth profile of area and area times condensate. So taking a big jump now to the bottom line, how does this work in the scheme as a whole? So this is single column model runs now forced with the same forcing as the LES runs. And I've plotted 4 important variables of the cloud fields here, averaged over in the middle of the day for these lasso cases. Notice that the LWP is on a log scale because it varies quite widely. So that's liquid water path. And I would argue that all of these are very good relationships, particularly if we go back to a few years ago where we had essentially no representation of subgrid clouds. So we're doing a pretty good job here. And I'm happy enough with this that I'm pretty close to declaring the 23-year project that I've been doing to get good subgrid clouds, particularly good shallow cumulus, into something like WRF. I'm just about to declare that finished. It still needs some tuning, and Joe will be working on that, but it's pretty darn good. Here's some profiles. So the same cases and the same averaging as on the previous slide. And we have the condensate on the top and the cloud fraction on the bottom, looking at the vertical profiles. And again, it's pretty reasonable. It's a little more interesting actually to look at the diurnal cycles. We tend to produce the cloud a little bit too early, and possibly not quite enough of it in terms of LWP later in the day. And from our point of view, since what's paying our salaries is the renewable energy program, we're interested in the short wave down at the surface, and that's the bottom plot. So there are probably reasons why the diurnal cycle is not perfect, and we can go into those if people want to ask questions or if you want to talk to me later. But we haven't completely solved that problem yet. So now to switch to the magic cases, they put the ARM mobile facility on a ship that went back and forth between LA and Honolulu in 2012 and 2013. I think they made 20 round trips. So I'm running now 3D WRF with ERA 5 initialization, including the 10-member ensemble that's provided by ERA 5. So the reason I'm emphasizing the ensemble is because I don't want to put a lot of development effort into small differences that are only due to the chaotic nature of the atmosphere or to the fact that a single deterministic run doesn't sample the reality completely. So I've plotted on all of these, I've plotted the gray background that shows the variation within the ensemble. And you can see that some of the differences are significant and some of them are not so significant. So the cloud base is significantly too low. The cloud cover is pretty reasonable. That's on the lower left. In particular, we have a good transition from the stratocumulus off the coast. This is plotted versus longitude. We have a good transition from the stratocumulus off the coast to a cumulus regime the rest of the way out to Hawaii. And that's not trivial. It's not that easy to get that. And you can see that, for example, ERA 5, which I've plotted on there just to show you what the initialization data is doing, ERA 5 is not getting that transition correctly. So we're actually improving over ERA 5. That scares me a little bit because I don't necessarily want my physics to produce the right answer if I give it the wrong inputs. But it's nice. You can also see that the ensemble is not super useful in the cumulus regime, and the reason for that is because at any given point, these are data extracted along a ship track. So at any given point, one ensemble member has no cloud, one ensemble member has a cloud. And so the range from the ensemble is 0 to 1, and that's not necessarily useful information. I need to find a better way to express that. The shortwave down is looking pretty good, and the liquid water path is kind of reasonable. Again, it's difficult to know how to look at that in the cumulus regime. Looking, however, at some satellite pictures. So we're looking down on the model now. We've got the real satellite picture on the bottom and the shortwave up at the top of the atmosphere. The interesting thing that jumped out at me right away on this, these are on a 13-kilometer grid, we're seeing these blobby clouds. They are partially resolved circulations. So this is a gray zone problem. And probably most people didn't think we had gray zone problems at 13 kilometers. But as Shia mentioned, the grid spacing does have some influence on what we can represent in terms of clouds. I can go to finer grids, which is what I've done here. I haven't run a lot of these at 3 kilometers. It does improve the structure. It doesn't necessarily change the statistics in terms of the outgoing radiation, for example. So for a climate model, you may not actually care about the cloud structure very much. I can influence the shape of the clouds by what I do with the parameterization. I can't completely solve that gray zone problem, but by strengthening the parameterization. So doing the opposite of what most people do when they think they're in the gray zone, by strengthening the parameterization, I can actually get a better representation of the clouds on the coarser grid. So conclusions, the EDMF updraft properties are useful in parameterizing shallow cumulus because they're strongly related to the cloud properties in the LES. We have a good source term and a short lifetime. The saturation deficit PDFs are bimodal or strongly skewed. So traditional methods of estimating that width is hard to get right. However, at larger cloud fractions, it's easier to get that right. I didn't talk about the vertical grid spacing, but this is an important point because it came up yesterday. Maybe if you're looking at weather, at deep convection, maybe you don't care about vertical resolution. However, if you're interested in stratocumulus, you need vertical resolution. I can't sustain or maintain stratocumulus in these runs, in the magic runs, even with the 65 level Rufus grid. I need the GFS type grid that's getting down to about 100 meters spacing in the cloud layer. I mentioned the gray zone problem. The gray zone is real. And we need to look some more at the interaction of subgrid and grid scale cloud, particularly in these magic runs where actually most of the cloud you see in those pictures is grid scale cloud. And I'd be happy to work with anybody who's interested in trying these cases with their own model configuration. So thank you.
Thank you. Question, comment?
and I'll be here all week, so.
Can you add a little more about the particle resolution?
Yeah, so I started out running with the 65 level Rufus grid, which has about 200 meter spacing in the cloud layer. And for stratocumulus, where you have that extremely strong inversion, the main problem was that the initialization from era 5 had clouds in it, but they were diluted too much in WPS, basically. And so the cloud wasn't there at the beginning, and then it would only slowly reform and at the wrong levels. So, but when I went to the finer grid, so if I get down to about 100 meter spacing in the cloud layer, then I've got a much better inversion, and the initial cloud water is not so badly diluted. So it's pretty, I don't think there's any way you can fix that with parameterization. I think that's just resolution.
Okay, thank you very much. Wayne. Next speaker is Sandra Legren we'll talk about satellite retrieving sheltering parameterization for dust event.
Okay, so.
Yeah, this is the holiday.
Okay. Okay. So surprise, they let a dirt person into the PBL session. So thanks for sticking around. My name is Sandra LeGrand. I'm a researcher with Army's Engineer Research and Development Center, or ERDIC. And our team has been working with desert dust modeling since the early days of WRF Chem. And our projects typically focus on improving simulated dust emission patterns. And we typically do this through two pathways. One is working on techniques to better characterize the dust sources, or where the erodible dirt is. The other is energy availability. If the winds are blowing, how much wind shear actually makes it all the way down to the soil surface? And how do you represent that in a globally portable model? And that brings me to this project, where we explored the use of satellite retrieved shadows to improve predicted dust emission patterns in the southwestern US. Right. This was a collaborative effort between ERDIC, UCLA, and the USDA. And I structured this talk to really focus on findings that I thought would be relevant to a broader NWP community. But we invite you to visit our paper in GMD if you're interested in delving further into dust world. All right, so most dust emission schemes are derived in terms of wind friction speed, or U star, since this parameter is related to wind shear stress. But roughness features, then that can be vegetation, rocks, fences, or even soil furrows, can shelter or attenuate the wind flow over the soil bed. Near the land surface, the total wind shear stress incorporates both the wind shear that's acting on the roughness features as well as the immediate soil surface. So U star can also be partitioned into roughness and soil surface components. And when it comes to sediment mobilization or dust emission, we really only care about the wind shear stress that reaches the immediate ground. So wind friction speed at the soil surface, or US star, is the actual parameter we want driving our dust emission schemes. All right. So for this experiment, we explored the use of an albedo-based drag partition that was initially developed by Chappell and Webb to estimate the US star parameter from the previous slide. Essentially, their technique associates the drag partition with shadows cast by roughness elements. If the soil is covered by a shadow area, then that soil patch in theory is being sheltered or protected by the thing that's casting the shadow. This approach helps us to represent subgrid scale roughness features in the model. And then we feed the time varying US star field directly into the dust lofting equations. All right, so the objective of this study was to evaluate the sensitivity of a dust storm simulation to this albedo or shadow-based drag correction. We used the Go-Kart dust transport and optics modules in WRF Chem version 4.1, along with the AFWA dust emission module, which has been part of WRF Chem since 2011. Our analysis used a convective Arizona case study from July 2014. Other authors have used this same Go-Kart AFWA combo and test case and found their simulations
I think this is a direct quote from their papers, grossly overestimated dust transport. And that seems to be a common complaint for people who have used this scheme in the Southwest US. So we wanted to see if incorporating this drag partition would improve the overall magnitude and spatial pattern of transported dust. Right. But because I'm a bit of a stickler for let's prove it, we added a bit of a twist to the experimental design and asked, well, what would happen if we just scaled down the winds in the dust emission scheme with a universal tuning constant? Right. So our case study event was a severe monsoonal convective dust storm that affected Phoenix, Arizona in July 2014. These kinds of winds, these kinds of convective events are super common in this part of the country during the US monsoon season, which typically ramps up in July and August. The top right image shows a storm summary with a radar overlay from 1 UTC on July 4th. The low level moisture and surface winds converged downslope in an area of elevated terrain called the Mogollon Rim, which initiated and sustained several convective systems that merged near and around Phoenix, which is let's see if I can figure out, use the pointer. There we go. The city that's marked with the X right there. The gust front at the leading edge of the convective cell that's south of Phoenix produced a wall of dust and near zero visibility conditions, with the worst of it occurring between 0 and 3 UTC on July 4th. Here along the bottom, there we go. We have hourly spatial plots of EPA monitored PM10 concentration data. And you'll notice that most of these stations are super tightly clustered around Phoenix. For this case, the dust wall just lights up the PM10 obs as it passes over the Phoenix metro. But once the main dust wall passes, the air quality conditions rapidly recover. And that's important in this case. So this is our model configuration info. My colleague, Alex Gallagher, who's hiding over there, she did a very in-depth tech report on how we selected this parent model configuration setting. We tend to spend a lot of time getting our environmental forcing conditions right, because honestly, there's no point in assessing a dust emission scheme if your winds are out to lunch. All right. So the original scheme effectively restricts dust emission to croplands, grasslands, barren and sparsely vegetated areas, and open shrublands, which for this domain translates to this, oops, it's a little bit off, this Z0 mask that's right here. For Arizona, this blocks the terrain from emitting dust in the forested mountain zones and the urban areas. But dust lofting is relatively uninhibited where the case study initiated. There's also a static vegetation mask that's built into the dust source strength parameter. And this is based on a vegetation climatology, pause for dramatic effect here, from 1987. And just so you know, that field is in every go-kart dust scheme that's available right now in WRF. We removed these masking features for our test configuration so that all vegetation controls and dust emission came from the newly implemented drag partition. This figure here shows what they look like when they overlap, with the light blue representing the erodible area. The problem is that the terrain in our case study area often looks like the real world image here, but the original model is treating it like the terrain and the image below. So if it's not masked out, 100% of that wind shear stress is going into dust production. And if you've ever been to a desert in the Southwest US, they don't look like that. They're pretty green. Our study also involved removing the dust source strength parameter from the emission scheme, but for the sake of time, we're not going to go into the details of that particular test in this talk. But I will say it's been really well documented that the default source strength field in WRF Chem is not very good for this area, and keeping it in the model with the improved drag partition suppresses just the dust emission entirely. But because this area for our case study storm has relatively homogeneous sediment supply, this particular case study is not really a good one for reviewing the effects of either removing or replacing the dust field. So that's something we're looking into under a different project right now. All right. Now, due to the convective nature of this event, we weren't able to perfectly simulate the environmental forcing conditions. The storm structure was spot on, so we got the morphology right. And the convective cell is in the right area, but the exact timing and movement of the storm were a bit off, which, still pretty good for this kind of phenomenon. But we wanted to better understand how these errors could affect our results. So we reviewed the approximate center of the leading edge of the gust front for both modeled and observed radar reflectivity over the storm life cycle. This thing is kind of off. All right, so this image right here, that kind of shows you how the tracks shifted during the duration of the event. But in short, the model event is a bit further north and rotated, and that spatial discrepancy reduces over time. But even so, that's something that we really have to keep in mind when we're evaluating modeled dust outcomes, especially convective ones against station observation data, when they're so kind of spatially clustered around cities. And because of that offset, we decided that our PM10 analysis really had to be qualitative, with emphasis on getting the order of magnitude right, rather than defaulting to what's typically considered more traditional statistical methods. And I will say that we stirred up a lot of controversy in the review process over this one. But honestly, when you take a critical look at the limited spatial coverage of these events and what those observations actually represent, using quantitative analyses really aren't appropriate. So these are simulated wind forcing parameters and a diagnostic we often use in dust world called excess friction speed for the peak of the dust event. Plot A is U star and plot B is the US star. The simulated total friction speed is generally an order of magnitude stronger than the surface partition, which is good. That means our treatment did something, so progress there. Plot C through E show that excess friction speed parameter, which we get by subtracting the threshold required to mobilize sediment from the wind forcing parameter. If it's blue, that means there's not enough wind energy at that location to pick up dust. If it's yellow, orange, or red, then you do have enough wind energy for dust lofting, assuming you have sediment available to loft. Plot C is for the control configuration without a drag partition. D is our experiment, and E is our globally scaled surface wind cheat. Immediately, we can see that practically in the entire domain is capable of lofting dust in the original configuration. But the ones that have some form of drag partition, whether it's a sophisticated one or a scalar, actually do restrict the dust to isolated areas, including the leading edge of individual storm cells. And I do find it interesting that our lazy scaling cheat didn't do too bad. These plots show the observed and simulated PM10 concentration for each test. To account for that storm shift, we also examined time series of the maximum PM10 simulated and measured values compared to the county area average that covers the Phoenix metro, since we figured the max value is almost always going to be along the leading edge of the dust wall, at least up until 4 UTC. So note the gust front in the simulation advanced into the combined county area earlier than the recorded event, and the real dust wall moves away from the EPA stations around Phoenix after 3 UTC. So if you take that into context for the time series plot, we would expect the simulated max values to be higher than the observed PM10 conditions before and after the PM10 peak at 2 UTC. So this kind of right at the end here, you can see that the control simulation is going bananas. It's not just wrong, it's very, very wrong. It's actually saying we're seeing more dust than the highest event ever recorded by an instrument. So that's wrong. But both the experimental and the cheat methods, they do pretty well, with the experimental treatment matching just slightly better with the observed concentrations. And it appears that the drag partition treatment is suppressing those broad scale erroneous dust emissions in Southern California and Southwestern Arizona, and that the control version is struggling with. All right, so summary, we did a case study. We used an albedo-based drag partition. As expected, the control model is producing way too much dust. Based on our findings, we believe that this albedo drag partition approach has the potential to improve convective dust forecasts in vegetated dryland areas like Arizona, but caveat. We might also be able to accomplish this with tuning with a global scaling factor. But that said, we picked that global scaling factor based on the input data to the parameterization, and knowing how to do that a priori every time you run the model might actually create more challenges. So regardless, I'm comfortable saying that incorporating some form of drag partition treatment to this commonly used dust emission module will likely improve dust forecasts, especially in the Southwest US. But a word of warning, you can't base a model performance assessment on a single case study event. So additional analyses are definitely going to be needed to confirm these results and that they're portable to different areas. So this study is really meant as a way to introduce the code to the broader community, and there's still plenty of work to do. I honestly think this would be a fantastic project for maybe a master's student or somebody to look at for reproducibility, and we'd be happy to help work with people if that's of interest. And if you're interested in learning more about the code or the papers or even implementation instructions, they're all here. So with that, I'd be happy to take any questions. Thank you.
Hi, Sandra. Very nice talk.
Thank you.
I was curious about grid resolution. So I assume your analysis was the innermost domain.
Yes.
And
yeah.
can you tell me what the grid resolution is? And then I was wondering
Sure.
if you looked at other grid resolutions and how it did in this effort.
So I'll go ahead and put this up, and I'm actually going to invite Alex to talk about that because we did do a sensitivity study on that. The innermost domain is 2 kilometers. So go ahead, Alex, if you want to touch on that.
Oh, yeah. So the resolution for our innermost domain is 2 kilometers. We did do a sensitivity study going under and over for 1.5 and 3 kilometers and found that when we altered it, it didn't get the storm morphology as correct. So we were focused on getting the actual spatial pattern and progression of the leading gust edge as good as we could. At higher coarser resolutions, the atmosphere just dried out way too quickly because there was a predecessor rain event in this case. So we had to maintain that high resolution to make sure that there wasn't going to be spurious precipitation from the upstream areas on the Mongolian rim.
And then just out of curiosity, how did the parent domain do, D01?
Parent domain did pretty well. So for the larger scale conditions, this was like a very synoptically boring event of just a classic high pressure over the 4 corners. So there wasn't a lot synoptically going on there. It came down to a lot more of like regional moisture inflows from both the the Bay of California and all the way in from the Gulf of Mexico across Texas into, there's like a little slot in the southeast corner of Arizona where it's able to channel in moisture content. And our domain 2 actually did a really good job of that.
Yeah, I remember like in some of our early experimental phases, we got better results by focusing on the parent domain and expanding it further out so we could make sure we actually were getting that moisture influx in, or else you end up with, I love this term, squishy rain blobs.
Yes.
So, and I think there's an important lesson here too, because a lot of the predecessor papers that we looked at, folks were verifying their forcing conditions by just looking directly at radar returns, which sure, that'll show you where the rain is, but that's not what's driving the dust event. So you really got to kind of think through the logistics of what's controlling the outflow boundary, what is the convective storm morphology. So just kind of a word of caution, take a grain of salt when you're looking at papers related to these phenomena for this part of the world. This is an incredibly diverse, multidisciplinary topic, and I don't necessarily think all the existing literature out there has kind of done the deep dive into each of the multi-factors kind of feeding into this truly interdisciplinary kind of topic here. But yeah, I honestly think the deep dive we did into the environmental forcing was where we spent probably about 80% of the case study part.
Just a quick comment. I imagine this happens elsewhere in the world too.
Oh yeah, yeah.
A few minutes late, but still before noon. This morning session is over. Thank you for all the audience.
Thank you.
Speakers. We'll come back at 1:15.
Hi, everyone. As we settle down for the poster session, may I ask the poster presenters who have sent in their one slide presentation for the lightning talks to come up to the side of the stage? Thank you. And just a reminder that our poster presenters will have 1 minute to present their poster or their lightning talk. Yeah, if you don't know, I have also All right, so we'll begin with our first presenter. Yeah, come on up and introduce yourself quickly and take it away.
Point.
Yeah, multiple slides.
아니요, point just.
Oh, pointer. Oh.
No. Right.
I don't
Let's
know,
forget
actually.
about that.
You know-
Okay. On the top. Okay. Okay. Good afternoon, everybody. I'm very honored to have you here for today. And my talking today is kind of just to investigate the relation between the nocturnal boundary layer and just pollution levels on the surface. And then we don't have any chances to just investigate the relationship on the same time series, like just PBR versus the pollutant levels, but we have any good chance to see the time series of these two issues during the Chorus AQ campaign. That's just conducted by the Korean EPA and NASA researchers, and we see some big differences between like just simulations and the observations. This is one example for this here. This is one example that's PBL time series. So you can see some like two PBL simulations, and then that line is the observations, and then the gray color is the nocturnal time area. And then we see some big differences between the observations and the simulations. So in turn, that's created the big discrepancies between the observation and the simulations here. So the low and very shallow simulations compared to the observations induced their big differences. So high nocturnal simulations compared to the observations. So this is another one. This is the second half of the period that we can see the same occurrences. So in gray area, we see the differences between the observations and the simulations, and it also created the higher concentration PM 2.5. So this is the some like just results for pointing out the discrepancies, not the solutions. But in this is all not all happen, but frequently we see some kind of like problems to predict the next day's PM 2.5 concentrations. So I just wanted to point out to see what's going on. So we have to do something to improve, to better simulate the PM 2.5 concentration. This is some last slide here. So we see this is for daytime sensitivity like a PBL height uncertainty versus PM 2.5 uncertainty. We saw non-sensitive issue in during the daytime, but in nighttime we're gonna have some very sensitive results. That's also depending on the PBL height uncertainty. The PM 2.5 is very much sensitive to that simulations. So probably that's the starting point to improve the PM 2.5 or the mixing processes in the nighttime. That's all we just prepared, and you can see and enjoy some another details for the relations between the nocturnal boundary layer and then PM 2.5. That's all. Thank you. Any questions?
I think we can save the questions for the poster browsing in a minute. All right, next up, we have Rafael Morones. Sorry about mispronouncing the name.
Good afternoon. Sorry, my bad English. The principal goal of this work is to present and introduce a new turbulence closure scheme. Previous two studies show that the two regimes boundary layers, stable boundary layer, is better represented when heat fluxes and temperature variance is solved prognostically. So the addition of those prognostic equations leads to better representation of stable boundary layer. Furthermore, the dependency of the mean and turbulent variable with the stratification arises naturally, not being more necessary an empirical stability function. So here I will present the closure scheme to turbulence and show the preliminary results simulation with single column model and a 3D simulation when I compare with the measurement from stations in the Rio Grande do Sul, Brazil. Thank you.
Okay, good afternoon, everyone. I'm Weiwei Li. I'm from NCAR REL. I'm also with Developmental Testbed Center, which is DTC. So as the title tells, in this poster, we're going to introduce some updates of CCPP single count model, including the parameterization simulator, where you can only run a single scheme with the rest forced by data models. And the second capability is the replay mode, where you can force the CCPP single count model using the full model output. So, and in addition to this part, we will also be glad to introduce an ongoing effort or a collaboration with the MCube physics group, where we try to connect the MCube shared physics, which is mesoscale reference suite, to the CCPP single count model. So, as some of you know, the CCPP single count model actually used the CCPP framework. So in this poster, I'll be presenting some results or demonstrating how we make sure the implementation is feasible by showing some results of comparing the two versions of YSU PBL scheme using clear sky and also cloudy condition case studies. So if you are interested in all of these, feel free to stop on my poster and look forward to chatting more. Thank you so much.
Hi, everyone. My name is Tomer Berg, and I'm a PhD student at the University of Oklahoma. So those of you from Oklahoma may recall this event from 2021. A major cold outbreak resulted in extreme cold across the East South Plains. And this cold outbreak was associated with not one, but two tropopause polar vortices, or TPVs, which are essentially small-scale vortices that tend to originate in the Arctic and can move out of the Arctic into the mid-latitudes, where they can produce a host of impacts, such as cold outbreaks. So in this case, we're looking at the impact of the TPV intensity on the cold outbreak. So we applied a modified methodology from Zabir and Cavallo 2018 to intensify or weaken the TPVs, as you can see in the bottom. And then we used those simulations to see the impact on the colder outbreak spatial extent, and magnitude in South Plains. And I'll talk about this more in my poster for those of you that are interested to stop by, but the main results are, it's actually nonlinear impact. So initially you do see an expected response of a stronger TPV equating to a stronger cold spool and more widespread cold air mass in the plains. But once the TPVs begin to interact and merge, this becomes increasingly nonlinear. And we no longer see a direct relationship between the TPV intensity and the cold air mass intensity. So if you're interested, feel free to stop at my poster. Thank you.
Hi, everyone. I'm Mei Wang from NCAR MCube. So my poster is about conditional object-based verification of MPAS medium range forecasts. In particular, we were looking at a set of variable resolution 15:3 global forecasts out to 5 days. It was an ensemble, and what we've kind of found was, and also highlighted in the previous, let me see if I can use this. Is these cold bias cases. And what we're trying to do here is using mode to identify convection errors, which is sort of highlighted here in these objects using the method for object-based diagnostic evaluation, and tie that back to large-scale forecast errors, as we know that the environment can also govern whether convection is sustained, initiated, sustained, and grow upscale. And I will add that in this study here, we've also done some case studies with our latest version 7.3, plus the fixes that was introduced yesterday, and found that a lot of these code biases have been reduced, as you can see in these subset boxes up on the edges of that first figure there. It's kind of blurry, but on the far right, I will also highlight on my poster some of these changes at different vertical levels and how it has improved with the different versions. I have some speculations on what have changed between these versions, so if you're curious, please stop by my poster and we can chat about it. Thank you.
Good afternoon, everyone. I'm Kent Knopfmeyer from CIRO NSSL in Norman. My poster will provide an overview of our MPAS convection allowing forecast that we started in earlier this year. And we did that because we wanted to try to assess its suitability as a die-core for the Warn-On forecast system. I'll point you all to session 10 tomorrow afternoon, where my colleagues will present some of our development activities and some initial subjective and objective verification work that we've done. I encourage you to look at the two websites in the next two bullets. The daily NSSL MPAS runs are viewable at cams.nsl.noaa.gov. And we also have subjective verification, which I have on the middle section of my poster that's at cams.nsl.noaa.gov/comparisons. And in the third column, my colleague David Dow at NOAA GSL has done some preliminary objective verification using their model analysis tool suite software. Covering the eastern half of the CONUS during essentially our hazardous weather testbed spring forecast experiment period. And I know I don't have any pictures on here, but I did upload my PDF, so hopefully all of you online can take a look at my poster later. Thanks.
Hello, I'm Russ Bullock. I work at the EPA in Research Triangle Park, North Carolina, and was hoping that animation would work there, but apparently it doesn't. It's already made the adjustment. But what I wanted to show to the sphere on the left is that when you're making the meshes for MPAS, a global mesh, a variable resolution global mesh, it actually moves points from all around the globe towards the area that you want your refinement. And that causes us some issues with some of our chemical modeling, because we want the background for a lot of our model studies. We want to use the same background simulation to provide boundary conditions for regional modeling. This is mostly for regulatory purposes. These backgrounds values have to be set and used over and over again for different scenarios. So what we're trying to finally get to is on the right, where we have a regional area in pink. That's our basic regional model domain, where we can then select points from a uniform global domain simulation around the boundary to set those boundary conditions. And my poster will show how I've found a way to actually make that happen. Thank you.
How do I advance the slide? Oh, there we go. Okay. Hi, everyone. I am Joseph Chan from NCAR. I'm an ASP postdoc here. Today, I'll be presenting a poster on behalf of Koichi Sakaguchi about the WRF Special Interest Group at the National Energy Research Scientific Computing Center. So this is a new user group in the new Perlmutter cluster from at NERSC. And the reason why we had to form this group was because it was really not easy for us to for every one of us to figure out how to run WRF on our own, because the computing environment was a fair bit different from that cluster's predecessor. And so we came together to form a group so that we can share our knowledge as well as some of the technical and scientific topics that we are applying WRF to. We have our own Slack WRF user channel and our Slack workspace, and we have been granted a small compute and storage allocation for the purposes of testing WRF and benchmarking it on this new cluster. And most importantly, we have a really nice set of instructions on how to compile WRF for this new cluster. And I can assure you that saved me at least 2 weeks of headaches. And now even better, WRF is now available as a module on this new cluster. So maybe all you have to do is just type module load WRF and you're done. So yeah, so if you're interested in this or the community stuff that we're doing for this new cluster, please feel free to drop by my poster, which is kind of hidden in the corner over there. Thank you.
Thank you to all the poster presenters for the lightning talks. So this session for the poster we'll have until 2:45 until our coffee break. So yeah, feel free to mingle and chat with the poster presenters. See you at 2:45.
Welcome to our session on tropical and precipitation studies. This is part one of a two-part session. The other part will be tomorrow. We have 6 talks. The first talk will be from Andreas Prime from NCAR M Cubed, who will talk to us about the water cycle over the third pole.
Thanks for the introduction and thanks for allowing me to speak today. This is not tropics, this is definitely precipitation, but we're looking here at the third pole region, which is the Tibetan Plateau. And as you can see here, there's a large range of co-authors. If you do a multi-physics, multi-model study, you really need to include a range of collaborators. And this project, this work happened under the convection permitting third pole CPTP project, which is a Codex flagship pilot project under the WCRP. And the aim of this project is really to advance hydroclimate research, especially in the climate change context over the third pole region. When we started this, I was really concerned because, as you know, this is a region with very steep topography, and I was concerned about model stability because we go down to 2 to 4 kilometers here. And we actually only lost 1 modeling system. So we still have 5 that were able to run in this region at very high resolution. This is WRF, of course, at high resolution and with multi-physics. We included MPAS in regional and global mode. We also have the Cosmos CLM model in a GPU version. We have ICANN, which is basically a similar code as MPAS. This is the successor of the Cosmos model. And then we have Rexium 4 as a non-hydrostatic version, which was released recently. What we're doing here over this common domain, which is the blue area, we are downscaling ERA 5 data to, as I said, to kilometer scales. Everything with the upper grid spacing was 4 kilometers. Some run 2 kilometers here. And if you ran on a very small domain on this blue domain, which we did with WRF actually, we had a 12-kilometer intermediate nest on in the red rectangle to have a bridge between ERA 5 and the high resolution. So this was really the first experiment. This is a 5-year project, and this is what we started with. We selected 3 case studies, and those are listed here. A flood-producing MCS in 2008. This is a 10-day-long simulation. Then a heavy rainfall producing monsoon event. This is more than a month-long simulation in 2014. And then we also have a heavy snow event in October 2018. So we tried to spread or span a large variety of meteorological situations in the region. And this is basically what I will talk about mostly today. And then we completed the water year 2020 simulation recently. And I only have one figure from that towards the end. So here, in the interest of time, I will mostly focus on this MCS simulation in 2008, which is fairly representative for the findings that we have. If you look at this region, it's really challenging, not only computationally, but also observationally. So this is a range of observational data sets for this MCS period, this 10-day period. This is accumulated rainfall. The MCS actually happened over here, this flood-producing MCS, but we evaluate the model in the whole domain here, so also including this very heavy rainfall in the foothills of the Himalaya. If you look at the models, how they did, the ICON model simulation by the Goethe University of Frankfurt was the best in capturing this event. You can see, like, compared to ERA 5, it does a pretty good job. This was global MPAS, which is really missing this event to a large extent here, but did fairly well otherwise. And if you go to regional MPAS, it looks much more like WRF. And most of the simulations that we looked at had this issue that the MCS is happening way too far in the south. And I come back to this later on. This was basically a vortex that spun up over the Tibetan Plateau, which was not very well simulated, which basically helped to attract the moisture further north. And this vortex is really hard to simulate in the models. This is just to show you the PDF of 6 hourly rainfall. This is from several stations in the study domain. The black line is the observations, the solid line. And you can see most modeling systems are able to capture that. I think you don't see the gray shading. Like WRF, the WRF model spread is basically between this dotted dashed line, the orange dashed line, and the upper line here. So depending on how you configure WRF with which physics, you can really spread the whole model range. Like you can really change how this PDF looks like, especially in the tail, depending on your physics, which is definitely not surprising. But overall, this high resolution simulations do a pretty good job in capturing intense rainfall, which you would expect from them. This is the only plot that I'm showing you for temperature analysis. What you see here is depending temperature differences at station levels compared to elevation where the stations are. And you can see below, like this, everything down here is below the Tibetan Plateau. It's working pretty well. Like we don't have, maybe a little bit too warm, but not too bad. Once you're at the plateau, all the models, except of one, which is the Cosmo model, have a cold bias. And this is fairly consistent for all the cases that we looked at. So we want to understand more why this is happening. There are probably some land surface processes that are misrepresented on the plateau. This is a busy diagram, but what's showing here is the spatial pattern correlation of this 10-day accumulated rainfall between comparing iMerge, which is down here as a reference, and all the simulations that we have. So ideally, you want to be down here in this corner. And you can see, again, like the observational uncertainty is pretty big. I wanted to break this down for you. So these are all the WRF modeling simulations up here. So if you change the WRF physics, you basically perturb, you go in this direction. So you basically introduce more or less variability, but you don't really improve a lot on the correlation. So it's really difficult with changing the physics to improve the pattern correlation of rainfall during this case. What you see as well, this is the global MPAS simulation down here, and it's really outperforming most of the WRF simulations, which is interesting because my initial guess was that you only get initial conditions and then you get sea surface temperatures, but that's it. The rest of the simulation is free running, whereas the regional WRF has lateral boundaries coming in every hour. Actually, the MPAS is doing really better. This is very consistent for the other cases as well. I come back to this later on. If you go from global MPAS, which are all the simulations down here, to regional MPAS, you still maintain the correlation coefficient, but you increase the spatial variability of rainfall. So you make it look more like the other WRF simulations from a spatial variability, which is interesting. So it seems like confining the model within a region is increasing the variability, probably due to boundary effects. Interestingly, like we have this range of WRF simulations over here. So there is one way to increase the pattern correlation, and this is by increasing the domain size. It's the only way that we found. And I come back to that because we have boundary effects on if you run WRF on the small domain. And if actually we did some experiments, if you further increase the domain size, it's actually getting better as well. Again, coming back to global MPAS, why it might be better because you don't have the constraints of lateral boundary conditions here. So this is a similar way of showing the results. This is again showing you pattern correlations, but now really correlating all the simulations with each other and all the observations. So red means high pattern correlation, blue would mean very low pattern correlation. So a few things to point out here that this basically says observations agree with observations, which is good. Like the patterns look fairly similar. WRF agrees with WRF, like you can modify the physics, but the patterns look fairly similar, except for a few exceptions in here. Like you see this columns here. Few of these settings didn't work out very well, but otherwise changing physics didn't change the patterns. MPAS looks a little bit more like WRF, but not a lot. Like these are all the MPAS simulations. So the other modeling systems are different from WRF, including MPAS. And then over here, all the models perform fairly similarly. So you don't see any modeling system really standing out, except maybe for this two, which is this icon simulation that I mentioned at the beginning. And these are the large domain WRF simulations, which stand out a little bit from the pack. So this is another way to summarize. This is another metric to look at. This is now the absolute precipitation difference over these three different cases that we had, the monsoon case, MCS case, and snow case. The lower, the better. The red point here is WRF, and the green point here is MPAS. So you can see in 2 out of 3 cases, MPAS is beating WRF. From the bias, and we see this also for other statistics. ICON is actually performing really well in all of those. This is observational uncertainties, just to emphasize. Observational uncertainties are really big in this region. It's probably half of the spread. Like the spread down here is showing you the standard deviation of these points. It's more than half of the model spread, is the observational spread. So really difficult region to evaluate the model in. Initial conditions, since we run this case studies, we thought maybe initial conditions like just natural variability, chaotic motions might contribute to these results. They're not really the dominant factor here. Like you can see, if this is a time lag ensemble that we ran with MPAS and WRF, and these time lags perform fairly similarly. So it doesn't really matter when you start the simulation. Then with WRF, we have multiple physics that we tested. The PBL scheme, we tested a lot of them, and YSU, UWCAM, and MYNN 2.5 were performing pretty well for all cases. If you look at the microphysics, 2 of them didn't really perform well, WDM6 and WDM7. The spread between the PBL and the microphysics, these numbers here are very similar. So if you change microphysics or PBL scheme, you get a similar response in the model performance. And interestingly, some of these combinations did not work out very well. For example, MYNN3 combined with WDM6 was really performing very poorly over the region. So just these are the last results that I wanted to show you why the domain size is so important here. And this is basically the mean chat location during the summer event, the MCS event. And you can see we're cutting through the chat directly. The D1 domain, even the D2 domain is probably too small. And with D3, we're getting at least northward of the chat, but we still have some boundary impacts. So basically just emphasizing that like a regional domain, running a regional domain here is really difficult, especially in summer. And this is just to show, this is from this year-long simulation that we ran at the end. And what you see here, the gray contour in the background is the observations that we have, and the thick green line, the red line is WRF and MPAS. And you can again see that MPAS, this is again a global MPAS simulation, is performing very similarly to WRF, even though it only gets initial conditions and sea surface temperatures as forcing. So it seems like MPAS global is performing really well. Just to wrapping this up, I was really impressed by how well global MPAS did. It often really outperformed the WRF simulations when it came to temperature and precipitation. It's probably because we're avoiding this lateral but boundary condition issues, especially cutting through chat regions seem to be a big issue. And one big surprise, no, maybe not surprise, but takeaway messages as well, like it's running more stable. If you run global, you can run MPAS at 24 seconds time step. If you go regional, you need 12 to keep it stable. And with WRF, we ran 15. So computationally, it's also therefore cheaper to run global. So from the 5 participating modeling system, I think all of them performed pretty well and in some way close to observational uncertainties, but this is observational quality, but this is also a testimony that the observations are really poor in this region. And it's really difficult to evaluate which model is doing good and which one is doing not so good. And with that, thank you for your attention and take any questions.
Hey, thanks for the great talk. I really loved it. So I have just a query regarding the lateral boundary issues which you talked. Like normally Rexium, when you simulate over India or the South Asia region, it just follows the South Asia Codex domain, which is pretty much different from the domain what you showed. It covers much more the southern part of India, and it also covers the Arabian Sea. So maybe I think that maybe if we can try the very same simulations of the South Asia Codex domain, it might work for you.
Yeah, so we had this discussion at the beginning, and since this is a community effort, and like we run at kilometer scale, so the problem is really if you increase the domain size too much, you lose most of the community because they cannot afford to run these simulations. So that's a compromise, yeah.
So maybe you showed it, but I actually have 2 questions. One is, how did ERA 5 itself compare? And the other is, if you had a slightly different initial condition. So for example, if you used one of the ERA 5 ensemble members rather than the deterministic ERA 5, how much would that change the result?
ERA 5 performed decently well. Like if we go back, like you can see this here as well, but ERA 5 in this diagram is, for example, this point down here. And then this diagram, see, like you see all this observations, ERA 5 is up here. Like they agree fairly well with each other. And I agree, like if we would use a different ensemble member, the differences might be bigger. For at least these case studies that we did. I think the monsoon case or the year-long case shouldn't matter because like if you get far away from the initial conditions, but yeah, for the MCS, it might depend on that.
So what LSM did you use, and why in the world can you get away with a longer time step with MPAS at the same resolution?
Like that's a very good question. Like my gut feeling is if you run globally, like you don't have, like I think the lateral boundary conditions are really causing instability in the domain. And if you run globally with a stretched grid, you eliminate those instabilities.
That's really interesting. And what LSM do you use?
We used NOAA and NOAA MP. So we tested both.
Over the high Rockies, we see this cold bias.
Yeah, I know, yeah.
As well, so.
Yeah, that's why I think it's really a land surface model, a land atmosphere coupling issue.
That could well be true.
A good point.
We'll get the answer now.
Yeah.
I think the lower time step with regional MPAS, that was the fix that we introduced in the version 8 release.
Oh.
It's an instability there because the boundaries are somewhat corrugated. So my guess is if we went back and redid it, we should be able to run that 25-second time step. And MPAS differs from WRF in how it time splits the dynamics relative to the scalar transport, which allows you to take that bigger time step. The dynamics time step is actually smaller than what WRF is taking, but you're making up that by taking a longer time step, fewer physics calls, fewer time steps for the scalar transport. So it makes sense.
Thanks, Bill.
All right, thank you. Okay, our second talk in this session is the only person who's not from M Cubed. This is Yaxin Shi from National Central University in Taiwan, and she will tell us about Typhoon Shantu's track.
Okay. Hello, everyone. My name is Yaxin Ji. I'm a graduate student in National Central
Apologies.
University.
Can you adjust your
Taiwan.
microphone,
Oh,
please?
okay.
Thank you.
The topic of my presentation is track evolution of Typhoon Chansu 2021 near Taiwan as investigated using a high-resolution global model. This study is conducted with Professor Huang and Dr. Skamarok. Here is my outline. I'll introduce track deflection and mention the MPAS model configurations. The results are divided into two parts. The first part is the simulation results, and the second part is about the idealized experiments, which are conducted to enlarge the spectrum of typhoon track deflection. However, because of the time limit, I will discuss some of the first parts of the results today. Many studies have investigated the track deflection due to the terrain effect. The channeling effect is well known. As typhoons approach the terrain may modify the typhoon's symmetric wind, leading to the track deflection. Using the PV tendency approach, Xu et al. 2018 found that asymmetric cloud heating plays a crucial role in track change. Huang et al. Highlighted the significance of the splitting flow around Taiwan, which causes the track deflection. This study was motivated by the Typhoon Chansu's track. Chansu moved northwestward toward Taiwan and deflected rightward near South Taiwan. After that, Chansu traveled northward along offshore of eastern Taiwan. There is a slightly leftward deflection as Chansu moves away from the northeastern Taiwan. Such track deflection may due to the Taiwan terrain effect. 2 days before the track deflection occurred, none of the tracks forecasted from the operational models captured the sharp turn to the south of Taiwan. That highlights the uncertainty in typhoon prediction when considering the interactions between the typhoon and the terrain. In this study, we want to investigate the track deflection mechanism of Chansu. Here shows the model configurations. We use MPAS to simulate Chansu during this period. This figure shows the grid mesh used in the simulations. The mesh with the highest resolution of 3 kilometers centered on Taiwan has used in previous typhoon studies. In this study, we further extend the resolution to 1 kilometer, also centered on Taiwan. Figure left shows the simulated tracks on the 60 to 15 to 3 kilometer mesh using different physical schemes. Most of the track capture the sharp turn, but are more westward in the later stage. We then enhance the resolution and conduct several experiments. The control run is denoted as CTL. It reveals that higher resolution reduces the track errors, and the sharp turn is simulated more reasonably. An inland track deflection is produced by CTL. This presents the leftward track in the observation at later time. The no-TW experiment refers to the simulation with Taiwan changed to ocean. Compare CTL and no-TW, it indicates that in the absence of Taiwan terrain, typhoon move more inland without the rightward deflection. The deflection may also be related to large-scale flow, so there is an experiment, no MJO, with the MJO mode filtered out, which results in a northwestward track. This figure shows that the simulations underestimate the typhoon intensity when compared to the JTWC best track data. And this figure shows the simulated wind field. There is a recirculating flow towards Taiwan Strait, stemming from the outer circulation of Changshu. The deflection occurs when the recirculating flow rejoins the typhoon's inner core from the west. As the typhoon moves northward, the flow shedding zone becomes smaller to allow more recirculating flow to provide more southerly flow. Unlike the presence of intense northerly flow caused by channeling effect for westbound typhoons, this vortex becomes weaker near the coast. Near this stage, the stronger flow to the east of the typhoon center is rotated to the northeast, leading to an inland check. In no TW, there is more symmetric cyclone. The cyclonic flow is much stronger and more easterly compared to CTL. At this earlier stage, the typhoon is driven in a constant direction. At later stage, the typhoon translation is similar to the best check, except for lacking of the observed inland turning near the northeastern Taiwan. Here shows the vertical motion at 3 kilometer height. At 63 hour, stronger vertical motion are primarily located to the southeast of the typhoon center, coinciding with the convergence zone between the typhoon circulation and the large-scale southerly wind. As typhoon moved northward, stronger upward motion rotated counterclockwise within the eye wall to the north of typhoon center. When the typhoon approached closer to the terrain, the horizontal wind is strongly influenced by the terrain, leading to the enhanced vertical motion between the typhoon center and the terrain. Because of the intense recirculating flow, the upward motion to the south of typhoon center becomes stronger. This upward motion decreases with height during this period. Without the Taiwan terrain, the stronger vertical motion also occurred to the south and east of typhoon center. However, the updrafts are not intensified at later stage. The difference in wave number 1 flow averaged at the height and in 1 hour is shown here to get more understanding of the steering flow. At 66 hours, there is westerly flow in the vicinity of the cyclone. An anticyclonic dryer forms to the east of the check, and the southwesterly flow is near the cyclone at 69 hours. In the subsequent hours, a cyclonic dryer is established, and the flow is southerly to southwesterly to the south of typhoon center. This pair of gyre rotate counterclockwise with time, resulting in southeasterly flow across the typhoon center. Such differences may explain why there is a check deflections in CTL. These are the evolution of the regressed translation speed induced by different wave number 1 PV budget terms. The details of the regressed method are shown on the right-hand side. In CTL, the translation induced by horizontal advection turn is dominant, except for the latter stage when the typhoon moves inland and its structure is strongly affected by Taiwan terrain. At this time, horizontal advection contributes to the northeastward component due to the larger positive wave number 1 PV located to the northeast of the typhoon center and advected by the westerly asymmetric flow in the inner core. Contribution from vertical advection terms increases with time in response to the stronger upward motions. The earlier translation induced by differential diabatic heating become more thoroughly at 72 hours, thus retarding the northward typhoon. This is a consequence of the counterclockwise rotation of the vertical convection. However, differential diabatic heating provide a northwestward translation at later stage, helping to drive an inland movement. This is in response to negative vertical differential diabatic heating southeast of typhoon center due to the stronger convective heating in the lower troposphere. At the same time, vertical advection also contributes some westward translation as a result of stronger upward motion west of the typhoon center. Impacts of both differential diabatic heating and vertical advection are combined to offset stronger northeastward movement by horizontal advection. This offers an explanation why a small inland movement of typhoons occur. In the absence of Taiwan terrain, horizontal advection turn is dominant during the entire period and gives more easterly eastward component than CTL, which is greatly offset by both vertical advection and differential diabatic heating, resulting in a westward motion at the early stage. In the end, there are some of the conclusions in this study. The MPAS model exhibits the capability to capture the track deflection, and using the enhanced resolution of 60 to 15 to 1 kilometer improves the track forecast. The simulations with and without Taiwan terrain and the wave number decomposition analysis highlights the terrain effect on the track deflection of Changshu. The PV tendency analysis shows that the rightward track is dominated by horizontal advection, while vertical advection and differential diabatic heating provide leftward translation. Here are my references. Thank you for listening.
We have time for a question. Okay, I will ask one. It was a very nice talk.
Thank you.
So I was interested in, it appeared that you had a simulation that you cut out the MJO, and that track, if I identified it correctly, that typhoon continued towards the northwest. It did not turn towards the north, towards Taiwan. Is that correct?
Yes.
Okay. So how did you cut out the MJO?
I just use analysis data about 90 days, and you put that data into the Lancos filter and filtered out about 20 to 60 days mode. And then I put this analysis data into the simulation.
Okay, so I think you also showed that the operational models were actually looking more like the no MJO simulation.
Oh, yes.
Okay, so the problem is the operational models aren't getting the MJO, are they?
Maybe they just think the MJO mode is not so stronger, I think.
Yeah.
Yes.
Okay, all right. Thank you very much.
Thank you.
Okay, our next speaker is Falco Ute. will be telling us about equatorial waves and precip in MPAS.
Thanks, Rob. Yeah, on the topic of MJO, I want to preface this talk by saying that I think there's a relatively easy way to really drastically improve our tropical weather forecasts. We just need computers that are 64 times as fast or as big as we currently have. Because when we have computers like that, how do I advance the slides, by the way? Oh, the middle button, okay. If we have computers that are 65 times as fast as now, we can run global models that look like this. That's a global convection permitting MPAS simulation on a 3.75 kilometer mesh, and it's really nice eye candy. We see hurricanes that look realistic. We see mesoscale convective systems in the tropics. So the global mesoscale is really at our fingertips with beautiful simulations like this. And I talked about weather prediction, tropics not doing so well, we're not doing so hot. I want to show you an example here. This is rainfall observations in a Havmüller form. So time is running down. That's about a 2 or 2.5 month period, and longitude is on the x-axis. So all these blotches that are tilted, that are actually moving features. Those are equatorial waves that actually make the weather in the tropics. And you see, there's actually a lot of variability. Often we think about the tropics being boring and it rains every day. Well, nothing is farther from the truth. There's a lot of weather variability in the tropics. So how do our current flagship models do? Very poorly compared to the observations if you think about there aren't really any propagating systems, right? So for example, in the GFS here, there is a stationary rainfall pattern. So at some points in the models, it rains 3 weeks straight. Whereas in reality, we have propagating features. So there's rain on and off. And the IFS, the ECMWF model, isn't really that much better. So our big hypothesis is this is a model efficiency that's related to parameterized convection. And to test this hypothesis, we created an MPAS resolution ensemble. We take MPAS, I think it was version 6 point something, straight out of the box, and we produced 10 simulations that only differ in horizontal mesh spacing. And the nominal simulation here is on the left. That's our 3.75 kilometer globally quasi-uniform mesh. So it's like your convection permitting WRF all over the globe. And then we successively increased the grid spacing all the way down to something that looks like a climate model from the 1970s. Was there a question? Oh, back to it. So there's 10 simulations, really high resolution 3.75 all the way down to really low resolution climate model type, but it's all using the same physics. We're running just one simulation 40 days long. That's where your compute power limitation comes in because it's really expensive simulating the global atmosphere at convection permitting scales. 40-day long simulation, summer of 2016. The initial conditions came from ECMWF and so did the SST fields. Just for the sake of simplicity, I'll only focus on 3 simulations here that I will contrast. The nominal convection permitting version of MPAS here, then 15 kilometer. This is supposed to be a placeholder for global NWP now. The IFS is around 9 kilometers, GFS around 13 kilometers, and then 120 kilometers. This serves as an example for how a CMIP type 1 degree climate model may look like. So how did these 3 MPAS simulations simulate the tropical weather for this 40-day period? We're going to be looking at Havmüllers again. Time is going up now. This is the 40-day periods, and this is longitude here. So in the observations from satellite estimated rainfall, you see all these propagating features nicely, weather variability in the tropics that's associated with equatorial waves. This is what the climate model version of MPAS sees. Similar to the operational NWP models, it just rains wherever the SST is warm, and there's very little in the way of these propagating features with heavy rainfall intensities. Actually, the 15-kilometer MPAS isn't that much better. So this actually looks similar to what the GFS would tell us. And if you compare it to the left, it's very far from the observations. Now we turn off the cumulus scheme, we crank up the resolution, and that's what we get. Something that looks much closer to the observations. There's really a step change going from 15 to 3.75 kilometers. It's really nice to see this. That's why I say, I think, we're used to tropical weather prediction is used to looking at this. If we could get here, we could do much better in the tropics. Just to quantify these Hofmüllers a little bit, this bar graph here is showing the variance of precipitation. So it's really just variance in a very broad sense. On the left here, we have the observations, and then here the 3 MPAS simulations, the convection permitting simulations, almost there. It's not quite there, but obviously much better than the 15 and the 120-kilometer version of MPAS. Just another point of view of how much better 3.75 kilometers is, we look at rainfall intensity distribution now. So that's essentially a histogram. We're counting grid points, and we see how heavy it rains in those grid points. These numbers here are pretty low. That's because these are actually pixels from the Hofmüllers. So they're 6 hourly averaged and 6 hourly average in time and 200 by 250 kilometer averaged in space, just to make those comparison apples to apples with all the observations and the model simulations. So that's what the climate model type 120 kilometer MPAS produces. This is 15 kilometers, a little bit better. And the big step change really comes, we're resolving convection, explicit convection, and it's really nice to see we're getting pretty close to the observations here. So again, the big step change happens when you're going from 15 kilometers where we still parameterize convection to something convection permitting, and we let the equations do the work instead of the parameterization. So this was rainfall. Now let's look at equatorial waves. And how do we look at equatorial waves? We're just filtering in space and time. I'm going to do this here. So this is the underlying data. Now we have filtered for tropical depression type waves. So we're just doing a Fourier filtering in space and time. And then we'll look at certain bandwidths. And this is what we get. Just for an eyeball comparison here, clearly we see that the 3.75 kilometer MPAS looks much closer to the observations than either of those two. And the effect is even more drastic if we look at smaller scale equatorial waves. These are westward inertial gravity waves. And clearly the 15 and 120 kilometer MPAS, they barely have them. The amplitude is much too low. But once we have explicit convection, the model seems to be able to capture those. Okay, so digging a little bit deeper into equatorial waves now. The way we do this is we imagine you were standing at a point on the equator. Maybe you would be one of these dots here. And then we have this. This is actually a Kelvin wave that propagates over you. Let's say we're starting out at the yellow point here, and there's this clock-like diagram. So 1 means you're in the trough. This is the suppressed phase. Here we have rainfall anomaly. So 1 is in the trough, and then the wave propagates over you. It goes around the circle here. The colors match in this diagram and up here. So once you're in wave phase 5, this is the green here. That's the peak of the wave, and we can see we have this nice a positive rainfall anomaly. So imagine you're standing here and the wave propagates over you. First it's dry, then the wave comes, it rains, then the wave passes and it's dry again. So now we're going to be looking at Kelvin waves from the 40-day simulation. It's averaged over all the waves that were in those 40 days. Kelvin waves, easterly waves, and inertial gravity waves. In black here, that's the observation. Again, that's iMerge. That's a satellite-derived rainfall estimates and just a sanity check. Rainfall anomalies are negative when it's dry and positive when we're in the middle of the wave at the peak and there is a positive rainfall anomaly. This is what a 30-kilometer MPAS was supposed to be 120 kilometers, but it actually doesn't matter that much. Anyways, this is coarse resolution, parameters, convection. There is some sort of a wave signal for all of them, but the amplitude is just not there. It's much less crisp than the observations. And similar with the 15 kilometer, and you can probably guess it, 3.75 kilometers is almost too good to be true. It really matches the observations pretty well. So I think this tells us that if we want to improve tropical weather prediction, equatorial waves, going to explicit convection is the way to go. So the last slide here, because it's not all positive, we're looking a little bit into the physical processes associated with these waves beyond just rainfall comparison. We care about rainfall a lot because it's an important variable, but is the model doing the right thing for the right reason? And what we're seeing here is a cross section on the left here. This is from the reanalysis. A cross section through, I think, an inertia gravity wave here. And here's our wave phase space again. So the active phase is here, and we see it before the wave comes. Now, inertial gravity waves are propagating westward. So if you're here, you see it propagating over you. It's starting to moisten up before the wave comes, and then there's the deep convection here. And then later on, after the wave peak passes, we have the moisture. The color shading is moisture here, and the contours are vertical velocity. So we see this nice buildup. First, the clouds are low, moistening in the lower levels, then deep convection arrives. And then after the wave passes, we have this kind of like stratiform pattern here where upward motion, the high troposphere, and downward motion in the lower troposphere. So let's just look at the pattern, so at the structure now. What we see in the observations is that there's this tilt that I just described, and that tilt also exists in the 3.75 kilometer MPAS version, but that tilt isn't there in 15 kilometers where we have parameters convection. So that tells us that the model is doing something right that is in the observations, era 5 quote unquote observations in terms of the structure. Now you look at the colors and you see it's much more bold in the model here. And the question is the model too bold, too strong in the wave activity, or is the reanalysis, which is not really observations, too weak? And remember, era 5 is built on the IFS model, so they use actually cumulus parameterization for their reanalysis product. So I think the jury still stands out if this is really too strong. It looks like too strong compared to the observations or reanalysis, but that's still a question that needs to be further looked into. And to finish here, I think I could all convince you that when we have a 3.75 kilometer global model, then we're doing much better with equatorial waves than with current technology, so to say. We're doing much better with more realistic rainfall patterns and rainfall intensity. And if we sum everything together into a feel-good message, is this that global convection permitting models have the potential to produce much better tropical weather forecasts and also climate projections. With that, I'd like to close and thank you very much.
I think I've seen enough that shows that better representing the organization and transfer of energy from the tropics to the mid-latitudes would greatly advance our predictability. I was wondering, you would look specifically at the tropics, but maybe in the mid-latitudes, would there be any more improved signals for anomaly correlation or something? And then to extend that, would there be a way to refine MPAS to have an equatorial refinement of the grid instead of like a circular one to help out with kind of these longer term, long range models?
Yeah, so to the first part of your question, I think we don't have enough samples yet to make this argument that there is really a big improvement. I think Cliff has his opinion that there is, but I'm a little bit more careful because we need a lot of simulations, preferably ensembles, to really tease out if there's an effect through teleconnections, better, let's say better MJO representation, better representation of blocking highs in the mid-latitudes. I think so far it's still a hypothesis. We need more cases to look into that. And to your second point, so I'm a big fan of quasi-uniform meshes because I don't know, I feel like they're more elegant than if you have mesh refinement, and yeah, you resolve convection in the tropics, but not in the mid latitudes. There's a lot of questions that come up. That's why I prefer the global uniform approach, but everyone can have a different opinion on that.
Okay, let's face it, we have an answer here. Convective parameterizations are no good. And that when we run a model like MPAS globally, a convective allowing resolution, we get this tremendous advance. Okay, let's accept that. We got it. Now here's a question that maybe we don't have. You didn't have an interactive ocean, right? So here's the question to you. I think the last question we have to answer is, to what degree do we need to have a coupled ocean? And at what period of time do we need it? Okay, so how far ahead do we need to have that coupled ocean to get these modes in the tropics and etc.? Do you have an answer to that, or
I don't have an answer to that
That's what
because
we
we
need.
don't have a fully coupled ocean at these high resolutions yet. So
that's what we need to do, right? That's
Yeah.
the next big step to
Oh,
explore.
no, I agree.
Because
I
we got
agree.
the answer for this. I mean,
I
let's
agree.
face it, this is
Yeah.
it. We got it, right?
I agree.
Yeah.
Hi, Falco. That's a great talk as usual. I have a silly little question about the TD diagram that you show. So the tropical depression half model diagram. Was it just me, or at about 180 degrees west? Like, I don't, did all of the,
this one?
Yeah, I was just wondering about that odd little blank spot at about
Yeah.
180 degrees west in the 3.75 and in the observations. It's like the 3.75 seems to be missing TDs.
So either you have very good eyes or you read the paper.
I haven't seen the paper.
Because it's actually in the paper. So it's true. So it doesn't capture those West Pacific tropical depression type waves. It really captures the ones up here. That's actually, these are African easterly waves. And that's right during the period of most active African easterly waves. And the model captures this activity, but it actually, there's a hole here. So that's, I think, partly why we're missing some variability here, because these tropical depression type waves are really making a lot of variance during the summer months. They're actually quite inactive during the winter, but we're missing them in the West Pacific, and I don't know why the model doesn't capture them.
Got it. Thank you.
Okay, let's thank him again. Okay, our next speaker is Kelly Nunez Ocasio, who will talk about tropical cyclone moisture sensitivity.
Thank you. Good afternoon, everyone. Today I will be sharing some results on moisture sensitivity experiments in MPAS with a focus of Genesis and African easterly waves. This is work in collaboration with Chris Davis from NCAR, Quentin Lawton from University of Miami, and Zach Moon from ERT. I want to acknowledge Rosimar Rios Berrios and Michael Duda for their help in the model setup. So in a recent MPAS model evaluation of the wave that became Helene back in 2006, we actually categorized this wave as a mixed off equatorial moisture mode, meaning that although this wave behaved like a moisture mode, so it was driven primarily by moisture, it still had characteristics of temperature being still a large contributor to its growth and tropical cyclogenesis. And so we proposed a pathway towards of TC genesis. And that pathway was mainly that the more these African easterly waves interact with the moisture and convection of the West African monsoon and the ITCC, the more moisture driven that they become. And that ultimately does help genesis. So we also documented that it was essential, the coupling between moisture and convection for the growth of this wave. Now, there were some unanswered questions, one of them being, will more moisture in the atmosphere allow for better moisture convection feedbacks that in turn help grow the system. In other words, if you add more moisture to the atmosphere, we see more moisture-driven types of growths and ultimately more intense genesis. And the other question was, how does moisture content affect the actual African easterly wave propagation? And so to do that, I came back to MPAS, this time using a limited area or regional configuration together with a variable mesh. So I used the 15 to 3 kilometer resolution variable mesh, and I used specifically the elliptical shaped, and I centered it over my region of interest. In this case, that was over Eastern Africa, Africa and the Eastern Atlantic. And so the 3 kilometer region is over this region where the African easterly wave propagated. And so the limited area configuration was because, well, I needed to alter the initial and lateral boundary conditions. So what I did, I took era 5 and alter it through the relative humidity. And so I had 4 moisture sensitivity experiments, the first one being control. I had a moist set of experiments, dry and very dry. Each set of experiments have 3 perturb ensemble members. So really it was a total of 12 simulations, but in the interest of time, I'll just show you 3 of the experiments here. And so the wave was tracked objectively in each of the simulations. So the total integration time was about 5 days and 6 hours. This is the time where the wave was propagating over Central Africa, Western, and moved into the Eastern Atlantic, just about when it was undergoing tropical cyclogenesis. So here I am showing you Hoffmuller diagrams. On the left of rainfall rate, so time on the y-axis is going upwards, and then x-axis is the longitude. And on the right is the Hoffmuller diagram of relative humidity at the 700 hectopascal level, and the counters are vorticity at that level. Note that I also added the track of the wave in those blue dots. So a few important things to note here. First of all, the moist simulation propagated slower, as we probably expect from theory. The driest propagated the fastest. Now, a few things to note here. The first one is the fact that although moist was propagating slower, what we find is that it was the control simulation where it ended up being more in phase with its associated convection. So as you can see here, the moist wave, the center of the vortex, was always slightly behind its associated convection. So we know for a fact from recent studies that this coupling is essential, and it turns out that the control experiment did have the stronger tropical cyclogenesis. And so was this related to that matter? Was it related to the changes in the mean state due to the changes in the moisture, or was it related to both? And so we looked at the zonal mean state. So these are vertical cross sections of the zonal wind for each of the experiments. And so we see here the features that we expect over Africa. We see, let's see, oh, here we go. So we see the, all right, oh, how do I do this? Okay, so that is the tropical easterly jet on the top. Right at the center at around 15 degrees north and around 650 hectopascal, we see the African easterly jet. And then right below that, that purple blob there is the monsoon. So we see that across the experiments. But what are the important differences here? Well, yes, indeed, the moist experiment had the more intense African easterly jet core in monsoon than control and dry. But another interesting difference, subtle, but it turned out to be relevant, is the fact that that core jet in moist was slightly shifted northward compared to control and dry. And so we hypothesized that it is that northward shift of the jet, although the wave remained propagating in the same location, is what inhibited some easterly wave jet interactions where ultimately eddy kinetic energies end up feeding the wave and its growth. So in the interest of time, again, I won't show it. It turns out when you look at the eddy kinetic energy, control simulation actually does have more available energy at the jet level than moist and dry. And so in addition of changing the intensity of the zonal mean state, by changing the moisture, we also see these changes in the propagation speed of the wave across the experiments. So here I am showing you a very simple scatter plot on the right, with x-axis being the zonal phase speed of the waves across the simulations. And then in the y-axis is the relevant mean flow. On the left, I'm just showing you a vertical profile of the shear, the zonal wind. And so if the changes in the mean flow were able to fully explain the changes that we see of space speed across the experiments, all those dots would be in that one-to-one line, and they're not. So although the majority of the changes in that speed of wave across the experiments can be explained with the mean flow, there's still an aspect of the propagation that comes from the internal wave dynamics and what's happening there. And so that's what we look at next. So just focusing on the top panel here, these are anomalies of diabatic heating in shade, and then the counters are of the meridional wind, and they're centered on the wave, and these are composites over land. So as you can see here, control is very evident that it was the more intense wave over land compared to moist and dry. What is another main difference? Well, the interesting thing here is that, as you can see, control had actually a larger fraction of deep convection, or the stratiform kind, close to the center, but also ahead when you compare to moist and dry. And so we believe that that smaller fraction of deep convection that happened in moist detrained it from the lower PV, detrained the mid PV from the lower PV, and ultimately also weakened the system. And so another way to look at this is just looking at the vertical mass fluxes. So those are plotted on the bottom for each phase of the wave. So just focus right now on the northerly vertical mass fluxes. We see that, again, the profiles of control in green have more top heaviness than in moist. In the northerly phase, that actually acts to help the propagation of the wave. So control was faster than moist. And then at the center of the trough, that is related to the maintenance of the wave. And so we see that the profile for the moist is more of a shallow type of convection compared to control, which had a more deep type of profile. And so very quickly, this aligns well with recent studies that suggests that a more saturated environment does not necessarily relate to a better chance of becoming a moisture mode. So if we add more moisture to the atmosphere, this does not translate to having more water vapor driven types of systems. And so my conclusions, again, more moisture does not necessarily enable moisture convective feedbacks. When you alter the moisture, the mean state over Africa changes in such a way that can alter the location of the jet, and that in turn affects the energetics of the African easterly wave. And finally, the changes in the internal wave structure are relevant for both growth and propagation of the system. As we saw, when we added more moisture, it turned out that it developed a smaller fraction of deep convection close to the center and ahead of it. And with the few minutes I have left, I want to say a few things. So that first paper in the motivation that I mentioned, this is data that is available at the Geoscience Data Exchange website at NCAR. So these are 15-kilometer horizontal grid global simulation. They are post-processed, meaning they are available in a lat-long grid. So you can use these data for studying globally tropical systems, MCSs of your preference. I'm working also to put these moisture sensitivity simulations in the same archive. And I quickly want to give a shout out to a forecasting tool that I've been developing during, it started off in grad school, and during my postdoc here at NCAR, together with my co-developer, we've made it an open source tool. It's the tracking algorithm for mesoscale convective systems, aka TAMS. If you Google TAMS MCS tracker, you find this documentation page. And the reason I mention it here is because we've made it in the independent grid type of tool. So that means that you can use it for both satellite data, but also for model data. You can use it in MPAS native grid or in post-process lat-long simulations. And so we have functionalities there. We have sample MPAS data, sample satellite data, and a lot of little functions that we help the user get the OLR from the model and calculate it and convert it into cloud top temperature so you can track systems. We actually used it over the summer last year for field campaigns precip and CPEC CV. MPAS was running the real-time forecast for both of these campaigns, and we had run TAMS on these forecast. And I think it really just added a layer of a forecasting to some certainty that the model was showing a long-lived system that perhaps we could be able to fly into, which was, for example, the CPEC CV mission-oriented type of field campaign. And so in that way, it can also be a validation type tool. And very quickly this summer, I have a student, her name is Tiffany Ortiz Rosario, and she is looking at these moisture sensitivity experiments, specifically focusing on the MCSs over tropical Africa and Eastern Atlantic. And so with that, I thank you for your time, and I can answer any questions.
Okay, thank you. Are there any questions? So I have one. So you showed in your moist simulation that the jet was positioned farther to the north than in the control of the dry simulations. And I'm not quite sure I caught the explanation for that. Can you remind me?
Yeah, so I mean, why it shifted to the north, I think it's related to the fact that the core was intensified. Why, how that translates to a shift in the north, I'm not quite sure. But I guess my point was that it is in that shifting in the north while the wave still propagated in the same location across experiments, where in the moist experiment, it kind of detached the weight from the jet. So it's no longer extracting energy from the jet, and that's why perhaps we saw a weaker genesis in moist, or at least part of the reason. The other aspect would be those internal dynamics and internal changes in the structure in the last few slides that we see.
Okay. All right, thank you. Any questions? Okay, thank you again. Okay, our second to last speaker is James Doan, who will talk about drivers of extreme precipitation events.
Okay, well, thanks for allowing me to present this afternoon. Yeah, so I'm going to talk about connections between extreme precipitation events. So I'm taking us back into the mid-latitudes and basically asking the question, why do extreme precipitation events come along in groups rather than randomly in space and time? So this is part of a larger NSF project. So I'd just like to acknowledge my collaborators at NCAR, Minga, Erin Towler, and Danielle Tuma, at UCLA, Daniel Swain and Jenny Bukowski, and at ETH, Manuela Brunner. Okay, a bit of motivation. Well, we know that extreme events are statistically and physically connected. So a few famous examples, we know tropical cyclones. If you look in the tropics right now, there's Brett and potentially Cindy that are connected because they're tied to African easterly waves. Another example, we know that winter storms come along in groups, may be associated with a persistent strong jet or cyclogenesis along the trailing cold front. And we know MCSs can be connected from one day to the next, associated with a MCV that persists overnight. Oh, one final example are families of atmospheric rivers that can be connected through extratropical cyclones or a setup for multiple Rossby wave breaking episodes. So and connections are not just scientifically interesting, but they're societally relevant. So I'll just depict that here in this schematic. So here's a blue probability space of the intensities of two events. So imagine if you are vulnerable to two high intensity events in that red square there. If these events are independent, you might be escape unscathed in this independent world. However, if we introduce some dependency between these intensities, the probability circle changes to an ellipse and it extends into your impact region. Okay, so where did we start in this project? Well, firstly, we created an historical data set of extreme precipitation events over the US. And we used ERA5 over a historical 42-year period. So we took the daily precipitation maps from ERA5 and converted them to binary as to whether they exceeded a threshold. And that threshold was a spatially and seasonally varying 99th percentile over all rain days. And so here's an example binary rainfall field. And then we connected the grid points that exceeded the threshold in space and defined the adjacent points as a single object. And we can attribute peak intensity, total rainfall volume, size, for example, to these objects. But for this study, we're going to look at the frequency of these objects over this 42-year period. Okay, so the one thing we can do is identify episodes of high frequency extreme events. So what you're looking at here along the x-axis is day of the year, and up the y-axis is year from 1979 to 2020. The colors are the 14-day event counts, so extreme event counts within a 2-week period. So if you just look at the Southeast US on the right here, you can see strong seasonal cycle in the frequency of extremes, the 2-week count maxima peaks in the summer associated with summertime thunderstorms, as represented by ERA5. Over in California, the 2-week event counts are much lower, and that's because these objects are much larger. You know, there are atmospheric rivers and winter storms. So what we did here, we want to explore whether there's a large-scale signature associated with these high-frequency periods that is distinct from climatology. So on the next slide, I'll just show you that indeed these high-frequency episodes have common large-scale features that are distinct from climatology. So this is for California now in the winter. So the climatology is on the left here. The black line is 500 millibar height climatology. You've got the famous winter ridge down the west coast and low-level moisture transport in colors and vectors. Now on the right is the anomaly of the composite top 10 14-day periods with the highest numbers of events. And this is the anomaly from climatology. So during high-frequency 2-week episodes, we've got a low height anomaly offshore, and consistent with that is anonymous moisture transport into California. So what I'd like to do next is to see whether this anomaly field for these clusters episodes is distinct from the anomaly field from more independent or weekly clustered 2-week periods. So I'll be working on that. Now that was looking at specific episodes, but now we can ask the question and go a bit broader scale and ask about the climatology of clustering. So now we're going to look at how these extreme events on a seasonal scale cluster from one year to the next. And so this metric we're going to apply is this metric of temporal cohesion. We renamed the statistical word dispersion. So if you think about the Poisson distribution of independent occurrences in an interval, this is shown schematically here. And so along the x-axis is the number of events within a season. And for the Poisson distribution, the variance of that distribution is equal to the mean. And so we have this metric of temporal cohesion, which is the variance over the mean. So that is equal to 1 if there's independence from one year to the next in terms of counts. However, a value greater than 1 suggests there's some clustering going on. So this means that a year with many extreme events may mean that the subsequent year also has many extreme events. So we applied this to our ERA5 based data set for this 42-year data set of extreme events. And we applied it by climate region and by season. And so wherever you see a color, it means that the distribution is not Poisson. It means that there's evidence for clustering. And so you see there's color everywhere. So extreme events are fundamentally clustered at this annual timescale per season. But the strength of the clustering varies by region and it varies by season, as you might expect with the different meteorological phenomena and drivers that are driving this clustering. So just as a reminder there, where you see, let's say, a bright red color, say a summer in the Rockies, that means that a summer with many extreme events means that it's more likely to be followed by another summer with many extreme events than would be expected by random chance. Okay, so now this is where MPAS comes in, because we wanted to ask the question, would we expect global climate models to capture any of this clustering that we're seeing in ERA5? More specifically, is clustering arising on the spatial scales represented by typical GCMs? So I'm suggesting that typical GCMs are about 100 kilometers, or in this case, 120. So we ran a pair of MPAS simulations for 30 historical years, one using 120 kilometer uniform mesh, and one with 90 refined down to 25 kilometers over the US. So each simulation is 30 years, and here's some details here. Initial conditions are ERA interim with SST update from ERA interim. And we actually ran 30 single year simulations to be more efficient on the machine and stitched them together. Okay, well, a quick sanity check that these simulations produce reasonable precipitation as would be expected at these resolutions, and I think they do. So on the top, sorry, the left column is winter, the right column is summer. The top column is ERA5, the average daily precipitation. The scale goes up to 8 millimeters. And then the other 4 plots at the bottom are the difference between the 2 MPAS runs and ERA5. So the difference fields are as expected. You know, we've got the usual coarse terrain effects at MPAS 120 that improves at MPAS 25, and we've got the usual dry bias in the Midwest that improves slightly at 25. But on the whole, I think it's a good enough data set to explore clustering at these resolutions. However, changing the resolution in MPAS doesn't just change the processes that drive clustering, it also changes the objects themselves that we have to account for. So here I'm showing on the top object number in these 3 data sets, ERA5 and the 2 MPAS simulations, going from September to August. So you see the annual cycle in object number, and it's much lower on the coarse resolution MPAS, as you might expect, and that's because the objects are larger, the extreme event objects. And that's shown in the bottom figure, where the average object number is universally higher than MPAS 25 or the ERA5 data set. Okay, so the question was, does a model at GCM resolution capture clustering? And indeed it does. So if you move your eyes to the lower panel, so on the left is winter, the right is summer. So at the coarse resolution MPAS, we do see some color here in this metric of temporal cohesion. So that means that there is some clustering operating, but the clustering looks much different to ERA5 at the top. So GCM resolution models do capture clustering, but it's different to a reanalysis product. It's also very different to a higher resolution MPAS simulation. So, and the higher resolution MPAS also looks different spatially to the ERA5. So at the moment, we're figuring out how to isolate the effect of resolution here compared to other, perhaps more interesting things that might be going on in MPAS as to the processes it represents driving clustering. Yeah, and I'll leave it there. So we've shown that extreme events occur in groups rather than randomly in space and time, and that's almost universal in every season, every region. There's a suggestion that high frequency periods of extreme events have anonymous large scale conditions. And it just showed that we might expect GCMs to capture some of these clustering processes, but at the moment we're figuring out whether that's a purely resolution, whether the difference with the observed clustering is a resolution issue, or whether there's perhaps more interesting things going on. And I think that the fact that these high frequency episodes have large scale signatures is an opportunity for extended predictability of extreme precipitation events. And that's the other half of this NSF project, where we're looking at exploiting these large scale anomalies to perhaps extend S2S predictability. So I'll leave it there. Yeah, thanks very much.
Do we have any questions? There is a question from Zoom.
It says, can we incorporate AI or machine learning for better prediction of these extreme events?
Yeah, I mean, this is a big data set, so it seems to lend itself to machine learning to understand perhaps the key variables and scales that are driving clustering. Yeah, that would be an interesting study. Yeah.
Isn't there a very easy explanation for all this? Extreme weather clusters, of course it does, because you have long wave patterns that set up, right? And that's true for certainly for atmospheric rivers, everything else. And the thing is, what drives these big waves, high amplitude waves? Often it's areas of convections in the tropics or in the Western Pacific that causes these wave patterns to form. So it all fits together. If we want to have predictability of extremes, we need to get the convection right, because the convection drives these big wave patterns, right?
Yeah, no, I agree. That's a great point. It's certainly a multi-scale processor. So you need multi-scales represented in your model and those interactions. Yeah, absolutely.
Yeah, thank you, James. I have a related question, actually. So you show that the clustering is higher in the high resolution simulation generally, but the high resolution is only applied over the US. But I thought, like, the clustering, my intuition would be that it's coming from remote locations, but the remote locations have low resolution in both. So how do you explain that?
Correct. We're only in the higher resolution MPAS simulation. We only have it over the US, so we're only accounting for local small scale contributors to clustering. We're missing remote small scale contributors, which ERFI would contain to the extent it's represented. Yeah, good point.
Any other questions? Let's thank James again. Okay, our final speaker of this session is Rosie Rios-Barrios, who will be telling us about the MPAS Aquaplanet simulations.
Thank you very much for the introduction, and thank you for the opportunity to speak here. I'm aware I'm the last talk of the day, so I try to keep this slide. We'll see how it goes. I'm a scientist here in MCube, and I've been using a capability called an Aquaplanet, which I'll tell you a bit about it today, to study different aspects of tropical weather systems. And so you may be tempted to think that tropical weather systems means tropical cyclones or hurricanes, but in fact, it encompasses a lot more than that. And something that's very special, unique, but also very challenging about tropical weather systems is that they span multiple spatial and temporal scales. So the main common unit of tropical precipitation is organized precipitation systems known as MCSs. These explain more than half of the precipitation in the tropics. And of course, embedded within them, we have the individual tropical convective updrafts. These systems, these MCSs, tend to be organized within synoptic scale and planetary scale disturbances called equatorial waves and the Malin-Julian oscillation. And these equatorial waves, even though they manifest in the rainfall, as we've heard in several talks in this session, they also perturb the dynamics and thermodynamics. And then if we look at the aggregate effect of all of these, especially if we take a look at the time mean, zonal mean state of the tropics, we have the intertropical convergence zone or the ITCC. So we have a lot of scales interacting with each other. And if you're interested in modeling these scales, especially in idealized frameworks, we need a modeling approach that can capture multiple scales, right? I'm interested in the fundamental understanding of these different scales. And for that, the literature has commonly used idealized frameworks, and that's where the aquaplanet framework comes in. So this is animation that's going to play out. The idea is that we take a global model like MPAS. We want convection permitting resolution, so we use a grid refinement so that we can have convection permitting in the tropics. We specify just a sea surface temperature that is meant to mimic conditions on Earth, but we remove land, we remove seasons, and we just let the model run. And impressively and amazingly to me, by just virtue of solving the model equations together with the physics packages, the model develops weather systems and a climate system that looks very similar to what we would observe in our tropical oceans. And something that is very advantageous of this is that we capture weather systems throughout their life cycles. So here you're looking at the formation of a hurricane. It just reached about category 3 or category 4, and it's about to undergo extratropical transition. And because we're able to run these simulations for several months, so this is a configuration with 3-kilometer grid spacing in the tropics and 15-kilometer elsewhere, I'm able to run these up to 4 months in the old computer. In the new computer, I'm going to be able to do several experiments that are more than half a year long, but essentially we get statistics. So we get statistics of weather systems, of how they form, evolve, and dissipate. And this allows many fundamental studies of tropical weather systems, but also of mid-latitude cyclones and many other oceanic phenomena. So I'll tell you a little bit about the implementation in the aquaplanet framework in case you're interested. It's really very simple. It's simply a test case in initial conditions. So instead of running WPS and creating the initial conditions, you just create the initial conditions. This test case specifies a sea surface temperature profile that is a function of latitude. It reads and user provided sounding, just like the idealized test cases in WRF. And then we specify resting atmosphere and other parameters that are needed. Then we run MPAS, and there is fewer than 20 lines of code really that go into the atmosphere core. And that's just simply to specify perpetual equinox. So essentially we don't compute the solar constant and the declination angle. We just fix the sun at the equator, and we specify zonal asymmetric ozone. And voila. There's no other major changes to the physics or to the dynamics. We just let the model run. And like I said, I've implemented these and I've used it. The experiment I've highlighted in these animations and this snapshot that you're looking at, these are with convection permitting resolution that I've been able to run for several months, but I also have other experiments with coarser resolutions that we can run for years, for several years. And it's just amazing that just using this global model, designed to study weather, we can also take a look at aquaplanet simulations, which have been traditionally done with climate models. And if you're interested in these, hopefully we will be including these updates in a later version of MPAS this summer. Oh, and by the way, in this screenshot that you're looking at, I'm not sure I can point here, that center, that rainfall core in the center, it's actually a Kelvin wave. So it's really amazing that you can just see the tropical weather systems evolve even with the naked eye. So I'll tell you a little bit about 3 applications so far of this MPAS aquaplanet framework. The possibilities are endless, but my collaborators and I have used this aquaplanet framework to take a look at several things. The first one is ITCC sensitivity to resolve versus parameterized convection. The second one, Falco talked a little bit about it, but also in the aquaplanet framework, we've been looking at the representation of convectively coupled equatorial waves in MPAS. And lastly, the last topic, which is a lot of work in progress and perhaps more on the scientific application, is the modulation of tropical cyclogenesis by Kelvin waves, which very much involves many multi-scale processes that benefit from having this global framework. So let me tell you about the first topic. So we were interested in looking at the ITCC sensitivity because many climate models are plagued with the so-called double ITCC bias. They produce a double ITCC when we expect a single ITCC, and there's many other issues with respect to the ITCC sensitivity. And so having this aquaplanet framework, and as I was developing it or implementing the code and testing it, it gave me the opportunity of doing what I call a hierarchy of experiments, where I have 4 different experiments. The first 3 are meant to mimic your climate resolution or high resolution climate model in the case of 30-kilometer cell spacing, 15-kilometer trying to mimic operational models, just like Palko spoke about earlier, and then that 15 3-kilometer experiment with 3-kilometer grid spacing in the tropics. So the first 3 experiments, I ran them for over 3 years. The last experiment, like I said, is only 4 months long. So we're going to be looking at statistics of the ITCC in the last 100 days of all of the simulations. And another major benefit is that we're looking at the ITCC, but like I said in the introduction, the ITCC truly is an aggregate of many tropical weather systems. So very big advantage of using MPAS for this purpose is that we can use model physics that have been thoroughly tested for weather. So model physics from the NWP community. So when we look at the comparison of these 4 different simulations, we find that resolved deep convection yields a single, more equatorward, stronger, and narrower ITCC. We can see that first here, looking at the relative frequency of the ITCC latitude. So essentially every day I checked objectively where the ITCC was in latitude. And here is a histogram of that. So we have 4 different lines with different colors, blue for the 120-kilometer, and going down in resolution or going down in grid spacing, increasing the resolution. The main message here is that if you look at the first 3 simulations, going from 120-kilometer to 15-kilometer, we're almost decreasing the grid spacing by an order of magnitude, and yet we get pretty much similar statistics. So all of the simulations with parameterized deep convection, they all have an ITCC that is about 4 degrees latitude. By the way, these are taken to be symmetric with the equator. So this is hinting at those simulations having a double ITCC, versus the 3-kilometer has a single peak at the equator, as we might expect from having a zonal asymmetric SST profile that peaks at the equator. So it's truly a step change going from the simulations with parameterized convection to the simulation with a resolved convection. The ITCC is also a lot more intense, and we can look at that by looking at how hard it's raining at the location of the ITCC. Once again, the first 3 simulations are all kind of clustered together. There is perhaps a little bit of change in the 120-kilometer with respect to the 30 and 15, but once again, the 3-kilometer seems to be the so-called outlier, but really is showing us a much stronger ITCC. And lastly, the ITCC is narrower. We see this by looking at the width of the ITCC in latitude, and that gray line is once again shifted from the rest, telling us the ITCC is narrower. So if you would like to know how we examine all of this, we did track organized precipitation systems. We looked at the equatorial waves, and then we arrived at an explanation for this, and I invite you to check out the paper if you're interested in the details. But essentially, we found that the organized precipitation systems were very different. They were more circular with parameterized convection versus more linear with explicit convection, and that has strong implications that we did prove that the convective momentum fluxes from the organized precipitation systems were different. They were up gradient with resolved deep convection versus down gradient. And without going into the details, that meant that in the 3-kilometer, it reinforced the shear, it reinforced the convergence, and it reinforced everything that I told you about. So essentially making up for a stronger, narrower, and more equatorial ITCC. Again, if you're interested in the details, I invite you to either come talk to me more or check out the paper. In the second topic is the representation of convectively coupled equatorial waves in global models. And I don't have to provide a scientific motivation for that because thankfully Falco provided a motivation for that early on. But the reason why we're looking at this is because MPAS turns out to be a very Kelvin wave friendly model. And we can see that in these Hofmüller diagrams. We're looking at rainfall rates average between 10 south and 10 north, and time is increasing up. And we have the 4 different simulations from 120 kilometers on the left all the way to 3 kilometers in the right. In all of the simulations, we do see rainfall variability, so there is propagation, and it's mostly driven by eastward propagating disturbances that propagate at about 15 meters per second, and that's associated with Kelvin waves. So there is a lot of Kelvin waves, but of course, if you look into a lot of details, just like Falco showed before in these aquaplanet simulations, the easterly waves as well as the inertial gravity waves are a lot more active in the 3 kilometer experiment. But the point is that all of the experiments capture Kelvin waves, so then we can proceed to ask, well, all of them produce Kelvin waves. Is the structure of equatorial waves accurately represented here? Not only to know whether the aquaplanet simulation is useful for looking at waves, but also to look at this resolution dependency. And so we use the wave composite approach that Falco mentioned before. The bottom line here is that when we look at these, we're sorting the observations, or the samples, we can apply it to reanalysis satellite and model data. And the key thing to remember is phase 5 is the convectively active phase. And so when we apply this diagnostic to the aquaplanet simulations as well as to the ERA 5 and IMERC climatology, we find that all of the experiments capture the overall rainfall structure, but the waves are a lot stronger with resolved convection. We can see that here we're looking at horizontal composites. So in the y-axis, we have latitude from 10 south to 10 north. On the x-axis, we have the wave phase. So remember, wave phase 5 is where the convective peak or the rainfall peak is. The color shading is rainfall rates. In the left panel is from IMERC, and the other simulations is directly from MPAS. And the streamlines are the low-level winds. So in all of the simulations, we have the rainfall rate where the heaviest rainfall rate should be at wave 5. In the observations, it's the peak is to the north, and that's because the ITCC is predominantly to the north. So we get that shift, but versus in the aquaplanet, we have an SST that's centered at the equator. But if we look at the low-level winds, the maximum convergence is happening at phase 5 in both ERA 5 and that 3 kilometer MPAS, but it's around wave 6 in wave phase 6 in the 15 kilometer MPAS, meaning that the convergence is happening much farther east, and it's not as coupled with the rainfall as we might expect. In the upper levels, we do get this upper level divergence that is nicely set up, but the devil's in the details. There's a lot of details in the vertical structure of these waves, and I'm not going to have time to show you all of the details, but we have found that a potential explanation explaining these differences between the waves is the different heating profiles, especially near and below the melting level. So looking at the Q1, which is a proxy for the diabatic heating, we have now 2 sources of observations. There are 5, as well as sounding data from Dynamo. What we see is, like, if we look at 15 kilometer and 30 kilometer MPAS, the ones with parameterized deep convection, they have a very sharp gradient below the melting level. And we have run the simulation without melting in the Tipke scheme, and that went away, which is suggesting that there is too much melting below the melting level, and this is having some implications for the temperature anomalies being decoupled, the rainfall anomaly, the water vapor anomalies being decoupled, and then resulting in weaker waves. So I've actually ran out of time, so I'll just tell you briefly that we've also applied these to look at the problem of tropical cyclogenesis and its association with equatorial waves. We have found that this simulation amazingly and unexpectedly can confirm a modulation of tropical cyclogenesis by Kelvin waves. So on the left, we have what we get from the aquaplanet. On the right, we have results from based on reanalysis data. And so essentially we're looking at how many days have passed since a Kelvin wave went by and then tropical cyclones form. And in both the aquaplanet and the observations, we do see a peak at around 2 to 3 days, which implies that the aquaplanet can capture the essential processes governing this relationship. So I'll leave my summary slide since I ran out of time. And thank you for your attention.